last no longer than 25 minutes. Okay, so Daniel, please go ahead. Thank you.
Yeah, of results from different groups. So I have results from H1, I have presented results from NNO, chat, and Apfelfast, and also a few more. I call this altogether determination of the strong coupling constant from chat cross-section. I will focus on chats. Great. Okay, so from chat cross-sections, so I consider 3 different kinds of chat cross-sections, all in leading order. These on the first side from chats in neutral current DAS, basically the recording chats like in neutral current DAS, and also the inclusive cross-section, or then chat production deep industrial scattering. This is a 2-to-2 process with 2 chats in the final state. And then also I have new results from LHC on digest production. So in inclusive DAS, we have discussed it on Tuesday a lot. What is about this HERA data, and there's a nice study from H1. Basically, what we have at HERA in inclusive DAS, we essentially measure just the scattering of the electron from the proton, and we don't care much about the hadronic final state here. And this cross-section has 3 ingredients: it's the F2 structure function, the FA structure function, XF3, and one obtains or one expects an alpha S dependence in the F2 structure function. I just want to switch on my camera. Sorry. Better. So in the F2 structure function has an alpha S sensitivity in NNO through the scaling variations, and by precisely measuring the scaling properties of F2, one expects an alpha S sensitivity. This has been done by H1 from HERA 1, and also by SUS, of course. Matthias, a nice plot which shows what happens. Basically, this is the H1 data, and it's a very, very shallow chi-square function as a function of alpha S. And essentially, the HERA data, at least the HERA 1 data, and so Q-square, they don't have a significant alpha S sensitivity. And this only comes then into play once one adds fixed target data from BCDMS, and then basically one exploits the scaling properties of the valence quarks and at high X. And by exploiting this F2 dependence, then one gets a very nice alpha S dependence, which is always obtained from ABM. In addition, there's the NNO, or the FA dependence, which is already leading order alpha S sensitive. And by measuring different center of mass energies, one can exploit the FA dependence and gets a sensitivity. This is done essentially in HERA 2. So there's the beautiful H1 and SUS combination data, which also includes these low energy runs. So here's the measurement of the longitudinal structure function from H1 and SUS, and this is all included in this combined beautiful HERA fit. And also here an IFS determination was done, and one sees basically again there's no sensitivity to strong coupling from HERA data itself, which is kind of a surprise, but this is just the fact. But the nice thing is that of course these data are very sensitive to the PDFs, mainly of course the valence quarks, but also the gluons, through the sum rules. And so basically everybody who takes the HERA PDF has only the PDFs, but without any additional IFS sensitivity from HERA. But of course, there's a lot of physics in DRS. So we have the recording chat, which did not got a lot of attention in the past, but now we started the program to understand also the hadronic properties and the QCD properties of the recording chat in DRS, and we have published our first measurement. Here we measure the chat azimuthal decorrelation, so basically the PT of the L triangle and the PT of the chat. It's an inclusive chat selection, every chat counts. Normalized with respect to Q, which defines the scale of the process. And then one gets basically 2 kinematic regions, the fixed order regime, which is here well described by NNO theory. There are also N3LO predictions available. And then basically these start to fail if one goes to low QT, where the resonation effects become important. Maybe also TMD effects can play a role, and this is not yet understood. And basically if one looks into multi-colour generators, which implement exactly these partnership models, then one gets a nice description of the data and also from the NLL prediction. And of course, these can be used in the future for IFS determinations, and we are also working on double differential measurement at the moment. But of course, this recording chat is a beautiful QCD laboratory, which is not investigated a lot in the past. And there are many more analyses at the moment ongoing. Recently started these are substructure measurement and subchats, room chats, which reduce the sensitivity to soft radiations, and individual particle quantities like hadron in chats, and charge energy correlations, or basically also just particle correlations inside the chat. And also directly measure, of course, the properties of the partnership by measuring the Lund-Tain or the KT splitting scales. So some of these measurements will come, at least on the cross-section level in DS 2022, but not yet exploited for an IFS dependence. But I think we should still have a look into these data, which have beautiful IFS dependence. I can measure it more inclusively. This has been done in the past, mainly in HERA 1 as a reminder. So basically, one can measure the event shapes And HERA H1 has published an IFS measurement which has a 1% experimental uncertainty only from the event shape measurements. Also, this used only a very limited data set, and only just HERA1 and only high Q-square data, but it's very limited by theoretical uncertainties. But since then, a lot has happened in the past on the theory side. Mainly basically in the SCAT formalism, new factorization theorems were developed, and one found new and more precise definitions of event shape observers. Here noteworthy is the one chattiness 1b, which is the thrust, but here's the thrust normalized with respect to q squared, not with respect to ET. And this ensures basically the infrared sensitivity of the observer and also makes the observer free from non-global locks. Contrary, it makes it a little bit more difficult to measure, but this is doable still with HERA data. And this has been done also here. See a first measurement of the one chattiness compared to fixed order prediction next to next leading order. These ones protected to the Born will become formula of N3LO. But you see basically the fixed order predictions are obtained large non-perturbative corrections. These are obtained here with Pythia, and the tail region here, or the TS region, already modern Monte Carlos have some difficulties to describe these. To exploit this one, IFS dependence goes back since long. So here Ian Stewart had shown this on a conference in 2014, where it shows the next to leading log predictions for the one chattiness. It also gives the sensitivity as a function of IFS. So by varying the IFS by 1%, also the cross-section varies by about 1%. So this case has to be expected linearly with IFS, at least in the tail region. These data is published now, or will be published triple differentially. So this gives, for the first time, also the inclusive TS measurement, but triple differentially, and this will open, of course, also new sensitivity in terms of PDF sensitivities. Sad enough, now coming back to chats, chat production in DAS. This is a 2-to-2 process. The reason is that basically one performs a boost, goes to the bright frame. In the bright frame, the photon here collides head-on with the parton from the proton. And to obtain a PT, it's a PT-dependent measurement, then basically one has to have a second hard emission, and this is basically sensitive to IFS already in leading order. Here's a summary of all the chat data. This always causes some confusion, which is available and which not. So one has inclusive chats, which basically counts every single chat, which has dichats, which basically measures the dichat properties. And these always come with two kinematic regions. The reason is because we have an asymmetric detector. Secondly, also we have trigger limitations and the cross-section scale with q to the power of 4. Therefore, one has a low Q-square data and high Q-square data. Typically, low Q-square data is more sensitive to IFS because they are the lower scales, and of course, we have the asymptotic dependence of the strong coupling constants. So we have data from early HERA measurements. We have then the full HERA1 measurements, and we have the HERA2 measurements for inclusive, dichats, and three-jet cross sections, low Q-square and high Q-square. And here the measurements published by H1 and by SUS. It's worthwhile to note that there are many more, particularly I think even more from SUS at the early date, but they are not available in next in order, but they can be exploited in the future. There are also 3- and 4-jet cross sections and forward chats and such things. But I will focus now on this data. So I'm focused first on the inclusive jet cross section. The reason is that this is a unique observable and equivalently defined for both experiments, H1 and SUS. So we can exploit these data for an IFS determination next to next leading order QCD. So the predictions come from N and the O chat here. We have small non-perturbative corrections because we have large cone sizes. The cone size of R equals 1, and we don't have pileup and another event, such things. And then basically we have a large amount of IFS values which come from every individual data sets. Early HERA data, HERA1 data, high HERA2 data, low Q-square and high Q-square. Similarly for SUS, you see that they are somewhat fluctuating, but overall you see a very consistent picture between individual experiments, between the two experiments, and this allows us then for combined determination of a strong coupling constant from inclusive jet data, and the best value that we get here is 0.1171 with below 1% experimental uncertainty. But on the contrast, we have large scale uncertainties because we are at comparatively low scales, about whatever 6, 8, 10 GeV. And then also we still have next to molecules these sizable scale uncertainties. And by restricting our selection of the data to higher scales, here we make a cut at 28 GeV. Then we somewhat balance the experimental precision with the present theory uncertainties in NNLO, and we get here an IFS value with an equally sized experimental theoretical uncertainties of 1178 with 1.5% experimental uncertainty, 2% theoretical uncertainty, which is mainly dominated by missing higher orders in NNLO. This also allows us for measurement of the running of the strong coupling constant. We can basically assign every single measurement a unique value and then determine the running and repeat the measurements. And then we get basically a running test of the running in the range from 7 GeV up to about 60, 80 GeV. At higher scales, basically both experiments contribute, and it's beautiful because one sees that they really cross-calibrate each other, and one benefits a lot from the combination here. There's a kind of a dimp in both experiments here. At higher scales, basically they start to deviate, but the average between H1 and SUS gives a very, very good confirmation of the running in this regime. And altogether, we have uncertainties here of the order of 2, 3, 4%. Then coming to digest, there's a limited or fewer data sets available, mainly 4 from H1. There's some missing, and also from SUS, there's one large data set which includes H1, HERA 1, HERA 2 data. This is also being measured all in next to leading order. We see that they have limited IFS sensitivity in the early data. But once it goes to HERA 2 data and to low Q-square kinematic regime, one has higher IFS sensitivity. And one gets also here an uncertainty of about 1.5% from a single data set. One can combine all these again from H1. One can combine it also with SUS, but here's the impact is very limited. So basically, this is essentially just a repetition of the H1 data. And then one gets from a digest measurement, one gets the IFS an IFS value of 1157 with 2% experimental uncertainty, 2.3% theoretical uncertainty. Also here, in running can be measured, which is then very similar to what we had seen in the inclusive jets because it's more or less the same data. One can also combine these two, and then one gets a somewhat a small improvement. The reason is that it's small because this data is highly statistically correlated. One can also go into 3-jet cross sections. Here, unfortunately, this is done only next to leading order because it's a 2 to 3 process with 4 colored particles in final state. And one sees that basically one gets from these 3 H1 measurements quite consistent results, but they have large experimental uncertainties, and also the theory uncertainties in NLO are very, very large. But I personally expect that this is just the next corner of fixed order NNO predictions. So we will maybe have NNO predictions also for the 3 jets in the near future. And this is then what we expect then experimentally from IFS extraction here. There's the normalized jet data. The trick here is that basically normalize the jet cross sections with respect to inclusive DIS. This basically retains the IFS sensitivity in the cross section, but it can't see some of the experimental uncertainties. In addition, we can't exactly with inclusive DIS, so with the data that constrains the PDFs. And by that, we can basically make use of these data in a combined IFS and PDF determination together with inclusive DIS data. So this has been done by H1. And we basically exploit all of these normalized inclusive jet and digest data, low Q-square and high Q-square data, together with all of the inclusive DIS data, which, as I have shown, have no IFS sensitivity on themselves. And basically from these jets, we get an IFS dependence of 0.1147 with exactly 1% experimental uncertainty. The PDF dependencies are small. The reason is, of course, that we have cancelled out some uncertainties, and also the PDF dependence in the jets are not important, and the scale uncertainty is dominant, which mainly comes from the low Q-square digest data. One word on HERA PDF. We have the combination paper where we have the HERA PDF 2.0 NLO predictions. This makes a quite a bit older selection. We have the inclusive jet, digest, 3 jets. We have also HERA 1 inclusive jets. We have HERA 2 and 1 digest, and also includes the charm data. And this gives some sensitivity, but one is limited, of course, from the NLO scale uncertainties. Recently, this was repeated in NNO, but the data selection is quite a bit different. So the 3-jet data are excluded. Low PT inclusive data are included. These digest data are excluded, and also these data are excluded. And as a result, one basically repeats the extraction from H1. And one has also the same experimental uncertainty. So here one is 1%. which is exactly the same number as one gets from H1 only result here. So this is beautiful consistent. So what will the future bring? The future brings us also new experiments. The LHEC is an experiment at 1.3 TeV. And here we expect a high luminosity experiment, 1,000 times high luminosity. And with these data, we can measure precisely the high X dependence of the inclusive DS cross-section. And this gives us a beautiful dependence on for the strong coupling constant. And we expect a measurement with the level of 2 per mil only once we have this data with full luminosity, of course, which is 1 inverse R2 Similarly, one can make an expectation what has happened to the jets. We have measured much larger kinematic range. So this goes up to several 100 GeV, while the HERA one is limited to 60, 80 GeV. We performed an estimation with all the full error breakdown. And this gives also an uncertainty of about 1 per mil. Also, the PDF uncertainties remain small in the future. So this is a beautiful pQCD laboratory. I think we should be pushing this forward. Similarly, we can also make a measurement of or an expectation of the running. For the running, one expect also the percent precision in level from say 7 up to 100 GeV, which then basically measures exactly the region where we at the moment have no precise data. So we expect almost a factor of 10 improvement with respect to recent measurements. So coming now to the present measurements. So these are the LHC dijet cross sections. At the LHC, we have proton-proton collides to two jets. It's again a leading order process, but this leading order process is now sensitive to IFS already. Leading order to IFS squared. There's some many more subtleties like underlying events, pile up, also harmonization effects. We take them all from the experiments. And the fixed order predictions here, for the first time, we exploit the next to next leading order calculations that are implemented in NNO-JET. These NNO predictions are interfaced to the program's fast NNO and API grids. So these store these predictions on a grid, and one can repeat them for IFS and PDF determinations. This is a work together with theoreticians, with people from CMS and Atlas. Here we exploit IFRS dijet data from Atlas at 7 TeV, from CMS at 7 TeV. From CMS at 8 TeV and from Atlas at 13 TeV. So this nicely balances different center of mass energies, 7, 8, and 13 TeV, different experiments, Atlas and CMS. These measurements come mainly as a function of the invariant mass. This is very interesting because invariant mass gives already a theoretically very precise or good indication also that can be identified as a randomization scale, which improves also the quality or basically the convergence of the NNO predictions. CMS Pich is a function of PT average, which has a close relation, at least to the invariant mass. And all these measurements are done double differentially, not all, as a function of the invariant mass and for different Y star regions. And CMS measures triple differentially as a function of PT average, Y star, and Y boost. This gives a higher PDF sensitivity, but here we want to focus on IFS in the following. Interesting, all experiments have a consistent jet algorithm. They all use the anti-KT algorithm, but with unfortunately with a different radius parameter. So Atlas here has a radius of 0.7, CMS is 0.6, CMS is 0.7. And for our 13 TeV Atlas data, we only have a small jet size of 0.4, which we conclude is basically the non-perturbative corrections become largely uncorrelated between these four data sets. So this is how we basically perform the IFS determinations. Very similar is done above in the for the NDS data. So here we want to really exploit the IFS sensitivity in these dijet data and with these NNO predictions. So we do not want to have any HERA or PDF sensitivity. And for that, we basically write down the QCD cross-section in the factorization using the factorization theorem. We have the hard coefficients and we have the two PDFs that convolute with the coefficients. We calculate the coefficients in NNO QCD, which are expanded obviously in IFS, and this gives the direct dependence of the IFS cross-section, of the IFS sensitivity, leading order, next leading order, next leading order. And also the PDFs has an IFS dependence. This is seen from the factorization directly. One applies the scale dependence of the PDFs. This introduces the splitting function, and splitting functions come with an alpha-S dependence. And now we want to exploit basically exactly this quantity for an alpha-S determination, and therefore we do exactly the same what the PDF filters do. We introduce a fixed scale, a starting scale, and from this starting scale we define the PDFs. Then we apply the decay kernels and evolve the PDFs to the scale where we convolute them with the fixed order prediction. And then basically exploit also this alpha-S dependence. And by doing so, we exploit the alpha-S dependence in the kernels, in the decay kernels, and also the alpha-S dependence in the part matrix elements. What we need from the PDFs is then only the X dependence. So here it's showing the X dependence that enters our alpha-S determinations. This is set at a scale of 30 TeV. It's kind of arbitrary, but we also include the PDF uncertainties. And by including the PDF uncertainties, in addition, we profile the PDFs and we exactly repeat the PDF fit, but adding additionally our digit data, but only with the sensitivity from our digit data. So this gives a very clean determination of the strong coupling constant from exactly this process, but including exactly the same methodology like the PDF fitters do. So first of all, we have to study the data consistency. There's a lot of discussion about chat data at the LHC, if they're consistent or not. Here we now perform individual fits to individual Y-star ranges for ATLAS, for CMS, for 8 TeV and 13 TeV data. And here's the chi-square over NDF of these fits. We also use many different PDFs to see that we don't have any PDF dependence. And we see that basically all these data are beautifully, or surprisingly beautifully described by the NNO predictions. The CMS here is a bit on the high side. Also, ATLAS 13 TeV data is very well described by our NNO predictions. For CMS, we see that there's the data with the high Y boost. They have an enhanced PDF sensitivity, and they particularly exploit the PDF uncertainties. But we don't want to determine the PDFs, but alpha-S in ideally most unbiased way, and therefore we exclude these high Y boost bins in the following and concentrate just on the central data, which have a reduced alpha-S PDF dependence. Also here we see from CMS 8 CV data that they're also very well described in NNO. So the chi-square here is about 1. Then we can do a common fit to all of these digit data. Here's a function for different Y-star regions. This gives a surprisingly beautiful agreement with the theory. So the chi-square NDF for these regions is about 1. And we also can test the scale dependence. As said, the invariant mass is very closely related to the scale of the process, to the randomization scale. Also, we see here an almost perfect agreement. So there's some fluctuation at high scales with the NNO predictions, and also for all of the presently available PDFs. And basically, when then doing a single fit to all of the LHC digit data, we get a very, very good agreement between NNO predictions and different for all different PDFs. So this is about 1.08 or so. So this gives our final IFS results from digit data next in order. We have here individual results from individual measurements. They fluctuate a bit about the world average value. They have somewhat larger experimental uncertainties. If you do the combined fits to all of the digit data, so these are 351 data points that we're considering, and we get an IFS of 1154 with about 1.4% uncertainty. PDF uncertainties are to some extent large, but as a big surprise, finally we have achieved that the scale uncertainties in these extractions are smaller than the experimental uncertainties and the PDF uncertainties. I think this is a big success of QCD. The results altogether similarly comparable to what Tony has shown on Tuesday for the inclusive chats. But this is also access to the running because MJJ is the randomization scale, and then we can do fits to individual ranges of the data. And we do the fits simultaneously, and by that basically constrain the systematic uncertainties. And then doing such a fit, we get here these, this is the running, I've zoomed in here a bit on the lower left side. We get an experimental and theoretical uncertainty for about 2% for tests of the running of the IFS of the randomization group equation in the range from 250 GeV up to 5 TeV. And even at the scale of 2.5 TeV, we have an overall uncertainty of only 3.3%. This is an outstanding improvement with respect to the previous CMS measurements here. And it's a beautiful confirmation of the running. In addition, of course, also we have here the digit data from HERA, which I have shown previously. And with these digit measurements from HERA and from LHC together, we test the running between 8 TeV up to presently 5 TeV. It's worthwhile to note that the 13 TeV data reach a level of up to 9 or 10 TeV. But we have only the early data, so they're limited statistics at very, very high scale, so we have to stop here. But I think the run 2 data give also access to the very, very, very high tail of the randomization multiplication up to 10 TeV. Summary, inclusive and judged DAS. So HERA data has no noteworthy sensitivity, but the future will give us a sensitivity once we have built a new experiment at CERN. And we expect here IFS sensitivities of the per mil level, both for inclusive cross-sections and for jet cross-sections. And we, of course, can do all this stuff with event shapes, substructure measurements, and all that. This is basically a beautiful QCD laboratory, which should be advertised. At the moment, we have jets in DAS from HERA. From inclusive jets, we have a value of 1178 with an experimental set to 1521 and so on forth. And a combined fit gets a bit better result with 1% experimental uncertainty. And recently, preliminary result on digit production from the LHC has a similar experimental uncertainty than the HERA data, but with a large reduced scale uncertainty. Importantly here that this is high scales up to TeV and this low scales at a few GeV. Okay, so this is my summary on IFS from jet production. Thank you very much.
Wonderful. Thank you very much, Daniel, for presenting these very interesting results. I see we have a few hands in Zoom. David, would you like to start, David?
Nice talk, Daniel. Thank you. I have a couple of questions. The first one is maybe, can you go back one slide, please? How do you take care of the top mass threshold when running the alpha S?
Yeah.
How is this taken care of?
This is as said here, this is an MS bar calculation with 5 masses flavors, and we at the moment we neglect the top contributions above the top threshold. Also for the plot here, the B and this jump threshold are not included in the plot. And what enters the fit is IFS MZ, 5 masses flavors, and then basically we evolve it back to the value where to the IFS value that enters the calculation at the particularly mu R value. But this is a master's calculation with 5 flavors.
But then eventually, I guess what you want to do is to use all this data to fit all this data here, and very nicely that we get up to 4 or 5 TeV. That's amazing. I guess that your plans are to fit all this data to the running of alpha S with a top mass threshold taken into account, running it backwards to the Z pole and extract alpha S there. Is this your plan?
Yeah, we have the main sensitivity. We have the IFS at MZ from the digit data, we have from the HERA data, and yeah, of course, we can combine them. Basically, this combination of these two. Interesting if in this determination, so we account for the correlation between the data, so they are published or they will be available. So basically, if one wants to make a test of the running, one can exploit the correlation between these individual data points. Then,
right, but you can do more than testing the running. That's what I'm saying. Yeah. And the second question, can you go to slide 16, for where you extract HERA PDF plus alpha S at the same time? Yeah. Shouldn't this extraction of alpha S go as a PDF extraction then? HERA PDF type of extraction.
This is the PDF extraction. Many has shown it on Tuesday, and this is also a PDF extraction. Yes. But these data are essentially the same as these data here. So
I'm thinking in terms of
depends on how you want to.
So we have a lot of other questions.
Okay. So in terms of category, yeah. Okay. Let's move on. Yes, thank you.
Okay. So Bogdan, would you like to go ahead?
Hello. Yes, very nice, Daniel. A first question on the LHEC. Can you comment on what kind of theory prediction, what order do you expect in order to reach that precision? I mean,
Yeah.
what do you
So
expect from the
for-
theory side in order to be able to have a similar precision as the one you quote here?
For inclusive DIS, it's difficult to estimate the fixed order prediction because it's a PDF fit, and I'm not aware of any reasonable estimation of fixed order. Sven maybe can comment. We expect N3LO predictions at the time when this experiment is done. For the jets, we have preliminary estimates on the scale uncertainties, but they had an issue with the double virtual contribution in the prediction. Therefore, the scale uncertainties are not exactly correct. So therefore, I can not exactly estimate the theory uncertainty. It's unfortunate.
Okay.
Sorry.
And yeah, just a small comment on the jet size on your choice that you do for the LHC data. So I understand from the perturbative calculation point of view why you want to have the broadest available jet size. Now for the non-perturbative, you have a competition between two effects, hadronization and underlying event. The fact that it happens to be small for 0.6, I would say is just by chance. I think what you should minimize is the uncertainty on this correction rather than the central value. I think this is what should drive your choice. I think your choice should be driven by the precision of the correction rather than by the central value, because it's just a competition of two effects. So it happens to be around 1 just by chance, I mean, for 0.6.
Okay, Simone, would you like to?
Yes, two quick questions. The first one is on the missing higher order uncertainty on your extraction from the digest mass. So this is also obtained with the offset method, so repeating the fit with varied scales, or is it by including the scales into the chi-square definition?
Yeah, it's basically the 7-point scale variation, but it's been tested. We basically calculate the derivative of the scale dependence at the nominal value and then extrapolate it to this factor of 2. And then we see a consistency with these data. So basically the scale dependence in the range between 0.5 and 2 is rather linear in the entire regime where we basically estimate the scale uncertainties.
But yeah, but sorry.
But it's not included, it's external, yes. We discussed it on the MetaMOS, it's not included.
Thank you, yes.
And not constrained by the data. It's just the propagation of the theory uncertainty to the value without the constraint from data.
And the second question is on this PDF dependence, because you include PDF uncertainties, but you don't redo the fit. And now you quote a single, so your final result is quoted with a single PDF, right? So my point is shouldn't you consider the spread of alpha S with different PDFs as an uncertainty, since these are all valid, perfectly valid fits, unless you prove otherwise, like that, you know, a given fit really cannot describe this data that you include.
Yeah. So this is a PDF fit, and we can also report the resulting PDFs, but we don't do it because we include the PDF uncertainties here, and this is exactly, so we add our data to the NN PDF fit or to the CTEC fit, because we have exactly the same degree of freedom and the same parameter space that they report from their fit, and we add our data. And this gives is a PDF fit. But there is a PDF dependence, yes, it's also seen here. Here it's seen. It's tiny. It's tiny. In terms of chi-square, there's a glimpse of preference for CTEC and for PDF for LHC. Any PDF what we have chosen here is a nominal PDF is basically, as a surprise, a bit outside of the range. And unfortunately, we see for the nominal result quite a spread in alpha S on the central value, depending on the choice of the PDF that we make. And this, unfortunately, here one of the largest uncertainties, yes.
So just one remark then, I mean, it's not really a PDF fit, right? If you were to redo a PDF fit, maybe you would choose a different parameterization, or you would enlarge your tolerances, or all of these things that, so, you know, you are assuming somehow that you are doing a small perturbation over the PDF fit. In that approximation,
we have the freedom from the NN PDF fit, and I think this is very flexible, or from MSHT. And in this degree of freedom that they report, of course, we add additional data. Of course, if they over-constrain the PDFs through the assumption on the parameterization, then we also underestimate a bit the PDF uncertainties.
Yeah, so I mean, all I wanted to say is that it has some approximation, this statement that PDF profiling is a PDF or reweighting is a PDF fit. Thanks.
Thank you, Simone. Can I ask quickly a question? Can you go back to 24, since we were at this slide? So there are some points that are barely visible. What are these X delta PDF? What does it mean?
So we include the PDF uncertainties, but we also perform fits without these PDF uncertainties. This is done essentially as a consistency check to see if the nominal PDFs that the PDF fitters report are consistent with our data, or if our data is only consistent within the PDF uncertainties. And we see that altogether, basically, our data is always in very good agreement with the central value for ABM. However, we need the PDF uncertainties to get a good chi-square, and also for N in PDF 3.1. So there's a tiny shift that our data would have on the central value of the PDFs. But this is mainly a cross-check on the consistency between the PDFs and our data.
I meant this around, okay, maybe I ask you later. So there is a question by Andre, and then one last question here from Pierre, and then we have to move on.
Yeah, thank you. I have a technical question to the next slide, which is page 26. No. Yeah, 26. Yeah, so to this plot, I have actually two questions. Just to understand, so when you use your theory codes for extracting the strong coupling, are the codes giving you values of the strong coupling at the center of mass energies which are indicated in this plot, or did you compute those from the results you get from your fits?
So basically what enters in the calculation is IFS MZ, and for the cross-section calculation, this is then evolved to IFS at MJJ. We perform the calculation of the cross-sections, but the fit value is IFS MZ. And then for this plot, we evolve the fit value back to the value that actually enters the calculation.
I see. I understand.
It's a technical issue how you.
Yeah, I understand. So, but this is
back and forth, and
yeah.
So
okay. But you say that the values of the dots are what's in the code actually somewhere.
Yeah. So basically, this is what's inside the code. And this is what we report here for the niceness of the plot.
Okay, a very quick last question now by Pierre, and then we have to
very quick,
move on.
So thanks for the nice presentation. I was on slide 25. I was a little bit confused by the fact that Atlas at 7 and 13 produced two very different alpha S values, while both data sets seems to have a good compatibility with the prediction. So I was wondering if you understand what is driving this difference, and whether if you put the two data sets together, the compatibility with NLO.
Yeah, so this is still preliminary. We have some understanding what's ongoing. Is one ingredient that enters, particularly unfortunate for Atlas, is that our NLO predictions have a remaining statistical uncertainty of about 1%. And for this 7TV data, this has a MJJ dependence, unfortunately. And this drives these data bits to the higher side. And for Atlas, this also goes further away. And without or with higher statistical precision of the NNO predictions, this would surprisingly be more consistent. This is a glimpse of some insights that we expect is happening here.
Okay,
thanks.
We have to move on. Thank you very much again. Ben.
Okay.
Thanks.
Yeah, thank you for your time. Sorry, Markus, for being over time.
It's a novel method for computing cross-section ratios in perturbative QCD. All of this is from the recently published article that you can find on the archive here. And the whole discussion is only about ratios. However, you see in this figure here, right? Ratios play an important role in alpha S determinations. And that's why it applies to this workshop. Usually, when we compute the perturbative QCD predictions for a ratio, and I call this the standard method, this is used in every publication that has done this so far. The pQCD predictions for the cross-section ratio are computed from the ratio of the fixed order pQCD predictions for the cross-sections. So this ratio of the fixed order predictions is not directly a fixed order result for the ratio R. And this is what this presentation is about, how to obtain a true fixed order result for the ratio. And then we compare the two results, the true fixed order results with this standard approach for different quantities, and then see what conclusions we can draw. So the overview over this presentation is, the first part is about how to obtain fixed order predictions for ratios, general methods for arbitrary orders and arbitrary quantities, and then specific formula for next to leading order and next to leading order calculations. The second part, we compare fixed order results with the standard results for 5 different data sets measured at the LHC and the Tevatron. These are these 3 multi-jack cross-section ratios. We use the observations there to identify systematic trends and then try to come up with recommendations for future pQCD predictions whenever cross-section ratios are computed. So in the following, you will find 5 slides with lots of formulas where I want to explain the method. It should not be too hard if you're here at this workshop. However, if you get lost at some point, you can join the discussion again at slide 11. So you will not miss anything substantial from this discussion. Okay, so let's start with the notation. We have a measurable quantity R. It's the ratio of sigma n over sigma d. N stands for the numerator, d for the denominator. But n and d are numbers, and n and d, they both denote the order of alpha s of the respective leading order contribution to the pQCD prediction. So for example, for R32, the numerator at leading order is order alpha s to the 3, while the denominator is order alpha s squared. So for the further, we assume that n is larger or equal than d, and we also assume that the ratio r is measured as a function of some quantity p related to the energy or the transverse momentum. In the ratio, both of the cross sections depend on this quantity, and p is chosen such that a simple function of it can be used to define the renormalization scale in the process. And that should be the same for both the numerator and the denominator. In the following, we will skip the p dependence, but this is essential, right? So that numerator and denominator both probe the same renormalization scales. So at the top, we see the standard formula for pQCD predictions, right? The cross-section sigma n is expressed as a perturbative expansion over all orders, where 0 corresponds to the leading order contribution, 1 to the NLO correction, and 2 to the NNLO correction. Usually K factors, an NLO K factor is defined just as the ratio of the NLO prediction over the leading order prediction. In terms of these pieces, sigma ni, we can write this as sigma n0 plus the NLO correction divided by the leading order contribution, or 1 plus this ratio. And now, instead of talking about the K factor, we subtract 1 and just look at this piece over here, which is the ratio of the NLO correction over the leading order contribution. And we call this one a reduced K factor. And so this is the NLO correction over the leading order contribution. And we can extend this definition now to all orders. We can define reduced K factors for all orders where the corresponding correction from a certain order is divided by the leading order. And with this, we can just write the top equation here like this, right? So every cross-section is then expressed as the leading order cross-section times 1 plus a sum of all these K factors. The leading order prediction for a cross-section is always uniquely defined, right? It's given by the ratio of the leading order contributions for the 2 cross-sections. And next to leading order, we see here the results for the standard method. We divide the 2 NLO results, or next to leading order, the 2 NNLO results. And as was stated before, these are not exact fixed order results. So what we try to achieve, a goal in which we write R really as a fixed order prediction in terms of a leading piece and then pieces in higher orders in alpha S, either like on the left side or here on the right side where the alpha S dependence is more clearly denoted. How do we achieve that? So here, let's do the calculation just for the next to leading order case. We can do this at every order, but at NLO, it's easier to follow here. So we start with the definition of R in terms of the ratio of the 2 NLO cross sections. Then we write this in terms of the leading order contribution and the modified K factors. And we write this in 2 steps. so that we have one piece over here and this fraction over here. The last piece will then be developed, expanded in the Taylor series, where the x is equal to the modified k factor for the denominator. And after expanding this, we can multiply the terms from the expansion with the terms that we have here in the parenthesis, and then we truncate the result by excluding all the contributions above next to leading order. And so the fixed order result at next to leading order is like this here, right? It's the leading order piece times 1 plus the k modified k factor for the numerator minus the modified k factor for the denominator. And all of these pieces can be computed from the results that we computed initially for the two cross sections. At the next to leading order, the calculation gives this result. And if you want to go to higher and higher orders, you can do that. And the general method for this is given also in the backup slides and also, of course, in the publication. So if you got lost in the formulas, let's just quickly summarize this. In the standard method, when we compute ratios of cross sections in pQCD, we take the ratio of the fixed orders for the cross sections, while here, in this case, we obtain the fixed order result for the ratio. So we have a leading order piece and a next to leading order piece for the ratio. Up to next to leading order, these two are identical. So the difference between these two results is of higher orders in alpha S. And with this being said, right, both of these methods are really on the same footing. They represent the next to leading order predictions equally valid. That means since they only differ in terms of beyond the next to leading order, none is better than the other. So if we say now this is the true fixed order result, this is just about the notation. There's nothing better about this result as compared to the standard result. So what we do now we want to see how these compare to each other and to experimental data. And we use these 5 different data sets, 3 from the D0 experiment, the CMS result, and the Atlas measurement. And just a note here, right? Everything that we do here in this case is for ratios of 3 and 2 jet production ratios, and it's done in next to leading order, right? As I said before, this can be done for every possible process and in every power in alpha S and at any precision, right? If you want Z plus 29 jets over W plus 13 jets, this equally applies to that. And if you have the ability to compute this, you can do this at this order too. So let's start with the CMS measurement of R32. This was measured as a function of the average PT of the leading 2 jets. And you see here now in blue is the computation according to the exact fixed order result. And the reddish band here, this is the standard computation of the ratio of the fixed order cross sections. So first you see that it's hard to see the fixed order result here because this is a very thin band and this is somehow hidden by the red band. So the fixed order result has a very, very small renormalization and factorization scale dependence. While the standard result, this is pretty much as what you have seen before in the CMS paper. So in this case, we see a perfect agreement between the two results. And we see that the fixed order has a much smaller scale dependence. This is not to say that the fixed order result is better again, right? This is just an observation here. Then D0 also measured R32, however, in a very different phase space. In D0, R32 was measured as a function of the leading jet PT, and it was explicitly measured for different requirements of the PT min cut, which is essentially the cut on the 3rd jet in the 3-jet cross section. And here we see something totally different. The standard result, this is what has been published with the D0 data, of course, this time with modified with up-to-date PDFs. But we see if we go to high PT-min, everything is described there. Once we go to lower PT-min, we see little deviations here when PT-max is getting small. This is the case now where PT-min and PT-max are getting small. So pQCD is not that reliable. That would explain this. Now the fixed order calculation is significantly below the standard result over here. And if we go to higher PT-min, it's getting closer and closer. But in all cases, the two error bands have no overlap. This time, so first, we see the total disagreement. The standard method describes the data. And now in this case, the fixed order result has a much larger scale dependence as compared to the standard result. Let's come to a new quantity. This is now the D0 measurement of the quantity R delta R, where we look at the average number of neighboring jets that surround a jet from the inclusive jet sample. And we measure this as a function of the inclusive jet PT, the distance to the neighboring jet, and the PT requirement on the neighboring jet. So here we see this as a function of the PT of the inclusive jet in the different areas here for different requirements of the neighboring jet PT, and then in each case for 3 different angular or Wi-Fi regions around the inclusive jet. And the data were originally published, of course, comparing to the standard method, and we see the standard method describes the data really well everywhere, except maybe here again, where the leading inclusive jet PT is small and the neighboring jet PTs are also small. And if we compare this, we again see that now the fixed order calculation again is in very good agreement everywhere with the standard method. So again, we see perfect agreement between the two methods. And again, the fixed order calculation here has a smaller scale dependence. Now let's look at this quantity R delta phi. This is the azimuthal decorrelation of jets. So we look at the HT, the sum of all jet PTs in the event, and we look what is the value of R delta phi. This is the fraction of jets that have a delta phi, where the leading two jets have a delta phi below this value, delta phi max. And we have this for 3 different requirements. And here now on this plot, there's a lot going on. So we measured this in 3 different rapidity regions. This is the rapidity difference between the leading 2 jets. So there are some cases, again, where we have a perfect agreement between the fixed order and the standard prediction. In all these cases, the standard prediction already had a rather small scale dependence, and the data were in good agreement with that. These were actually the regions that were taken. No, sorry, now I'm confusing 2 things, right? So here there's the data are well described by the theory, the standard theory, and the standard theory has small uncertainties. And we see again in this case, as before, where this was the case, that the fixed order calculation agrees here with the standard one and has much smaller scale dependence. Then we have these 3 regions here, where we have a rather small delta phi max requirement. Here we're running slowly out of phase space in the next to leading order calculation. And first of all, you see that the variable, the quantity is much smaller here, right? So it's very few jets that pass this. The standard method here has already a significantly larger scale dependence. Now the fixed order method is, I would say, in partial disagreement, all right? The central values are kind of away from each other, but the 2 error bands, they still overlap. And I think both describe the data really equally well and pretty much at the edge of their uncertainties. And there are 2 regions left, those here. In those regions, the data have a very different shape as compared to the standard method for the calculation, right? The data, they go downwards, except for that last bin over here. But, right, we're used not to judge the highest PT bin too much, right? So let's not be irritated here by that. I think other than that, the data have clearly a different shape as compared to the theory calculation there. while the fixed order calculation here gives a very nice description actually of the whole shape. And this quantity was later then also, I'm losing my cursor, here's my cursor. This quantity was later also measured on Atlas. And it's funny, right? If you switch between the two pages, you almost don't see any much difference, right? But this is now the Atlas measurement, and exactly the same what applied to the D0 measurement also applies to the Atlas measurement. These are the regions where we have perfect agreement over here. These are the regions where the two theories, just the error bands overlap a little bit. And these are the regions here in which, again, for Atlas 2, right, the shape of the data is clearly better described by the fixed order result as compared to the standard method. So now let's try to summarize and find some trends here, right? So we have cases in which we have perfect agreement of the two theories. This was for CMS R32, D0 R delta R, and some kinematic regions in the D0 and Atlas R delta phi measurements. Whenever the two theories had good agreement with each other, there was also good agreement with data. And in all these cases, the fixed order had a much smaller scale dependence. And there were some regions where they disagreed with each other, the D0 R32 and some kinematic regions of the D0 and Atlas R delta phi data. In those cases, it was always one of them that agreed with data, but it was not always the same that agreed with data. And in those cases now, the fixed order result had a much larger scale dependence as compared to the standard method. And then we had those two cases in the R delta phi measurement where the two theories, they agreed on the edge of their uncertainties, both somehow agree with data, and both have now larger scale dependencies as compared to the other kinematic regions that we discussed before. So just a reminder, right, what we said before, none of the two predictions is fundamentally better or preferable for some reason. They are really both on the same footing, and any difference, therefore, should really be regarded as an uncertainty of the next to leading order result, right? Because the differences are due to higher order contribution. And the reasoning is very much the same as what we usually use for the scale dependence. And while we say the scale dependence somehow reflects higher order contributions. So based on this, I think it's rather straightforward how we should treat these calculations. I would suggest to compute both the fixed order and the standard predictions. Which one should we use for the central value, right? Maybe the one that gives the best chi-square to data, and in many cases, this can simply be done by eye, right? Very often the question is, right, is theory able to describe the data? And then, of course, we should give theory a chance, right? Let's take the calculation that gives a better description. However, for the uncertainty, we should always, I think, use the envelope of both bands, because the difference of the two calculations is still an additional uncertainty on top of what we compute with the scale dependence. Whenever the two methods agree, it's easy to make the first choice about the central values as they agree anyway, so it doesn't make a difference. However, the uncertainty band, in the cases that we looked at here, right, where the fixed order had a much smaller uncertainty band, right, so that therefore in the future, the uncertainty band in this approach will still be dominated by the standard approach, so there's no real change. However, if we have cases where the two methods disagree, of course, the choice of the central value will in general improve the agreement between data and theory, and the increased uncertainty band gives certainly a more realistic estimate of the true uncertainty of the calculation instead of that simple choice by just looking at the scale dependence. So that will mean in the future we will probably get better agreement if we approach this method, and the uncertainties will be more realistic, larger only in those cases where we were in trouble anyway. So how would this affect if we had done this way, how would this have affected the 5 analysis? The CMS R32 analysis, there would not have been any change, since the uncertainty band of the new method is always inside the uncertainty band of the standard method. In the D0 case, we would have remained the same central values. However, the uncertainty band would have significantly increased because the other theory is significantly off. And that would have been, this would have correctly addressed the large additional uncertainty that we have in this game. In the D0 R delta R measurement, there would not have been any change. And in the D0 and Atlas R delta phi measurement, it depends then on the kinematic regions, and we are, right? But in all cases, this would have been a positive effect on the comparison of data and theory. Maybe just last comment. Of course, for other variables, for other quantities, this does not maybe have to be the case, right? These similarities that we observed here. But I think since the fundamental concept is so simple, right, of the recommendation here, I think in all cases, analysis will improve by using these. Okay, thank you very much.
Thank you very much for this very interesting presentation. I already see a number of hands. David, would you like to start?
Yes, thank you, Markus, for this nice talk. Shouldn't we just then go to the NNLO calculation? I mean, we would get rid of, I mean, the fixed order result would be better in this case. And this will probably improve the agreement with all data sets. So what prevents us from doing a full NNLO analysis for the ratios?
I'm sorry. Of course, NNLO is always better, right? If we have these theories at hand, right, let's do it. And the point here about this method, I mentioned this somewhere, right? This is not restricted to next to leading order, right? So if you have the NNLO calculations at hand, you should do the same, right? Here's the formula, how to get the fixed order result for the ratio at NNLO.
Yes,
And
so do we have the NNLO results or?
No, we do not have these, right? For the 3-jet cross sections,
the 3-jet, not yet.
Okay, no. And what is that? I see. But we have them for the 2-jet, of course.
Yes, right.
Yes, I see. So, Julia, what do you think is the time scale to get the 3 jets at NNLO?
No, I mean, I think the point here of Markus is that one can do this regardless of for any type of calculation, that even if you had an NNLO, you could do this procedure on your NNLO. So you somehow, it's so you have an ambiguity when you define ratios, and you can use this ambiguity as an extra source of uncertainty. This is the point. So of course, you can apply this on whatever is your best prediction. I mean, one of maybe a question that I had here is when you take these ratios, I mean, the point is that they have small uncertainties in your plots. And these small uncertainties come from the fact that they largely cancel because you vary the scales in a correlated way, for instance, in your ratio. The other thing one could do is vary this in an uncorrelated way. This would also enlarge this uncertainty. So, I mean, I think it's true that when you take ratios, and this we know very well, also from cross sections with jet vectors and so on, if you just take these ratios and do a scale variation, you typically get to small uncertainties. And so I think this is a way to probe this. Do you understand this correctly, Markus?
I'm not sure. So did you suggest to vary the scales independently? I know this has been proposed, but I'm very much against that.
No,
but
I'm saying that if you just take the ratio and you just vary the scales, you get typically cancellations on
Right.
this ratio. So you typically get two small uncertainties.
No, I would not say that. That the point is, if you take the ratio of a 3/2 jet cross section, right? 3 jets, they were proportional to alpha s cubed. Well, the ratio is only proportional to alpha s square. So it's just natural that you get a small scale dependence. I would actually argue you get the correct scale dependence.
But at the end, what we all want is to derive alpha s at NNLO. So we don't. I mean, yes, we can. By doing this, we now understand what the uncertainties are the correct uncertainties are for NLO result, but this will not bring this. These ratios will not provide an alpha S extraction at the level of accuracy that we want.
If you go back and show your results, Markus, can you show your results when you showed these three cases?
Sorry,
I mean, at some point you had these three. One thing later, you're somehow with your hand written the three regions essentially. Yeah, here. I mean, you see also in the region where you say that. Total disagreement. I mean, it's not a total disagreement. I think here it's really that the band is very small, right? In my opinion,
but
for the standard, I will not call it total disagreement, to be honest.
This one here.
Yeah. For instance, there is one point which has a large uncertainty.
I'm not talking about the data now. I'm just talking about the two theories. The two theories there are.
Fine, but even the two theories. I think the point here is that one has a very small uncertainty, too small. If you enlarge this uncertainty, then it will not be a total disagreement. But sorry, I don't want to. There were also other questions. Sorry. So there is a question by Klaus and then Bogdan.
I think Bogdan was before me.
Okay. Well. Okay, then Bogdan first, sorry.
Doesn't matter. Hello, thank you, Markus, for the nice talk. I have a comment. I recently looked into a paper by Gregory Soyers from 2011 on cross-section ratios with jets with different sizes. And I think he makes essentially the same argument about the way the calculation should be done. But his conclusion is that this new way of, or this improved way of doing the calculation actually allows to correctly compute one extra order in alpha S. So from his paper, I didn't get this conclusion that both calculations should be on the same footing, whereas you actually insist quite a lot on this. So I'm not sure how one should put the two conclusions together. Have you looked into that?
No, wait. Bogdan, this is something different. If you compute the ratio of two cross-sections with different jet definitions, in that case, the leading order results, they are identical. And based on that, this is what you could do, right? And this is different from what I'm presenting here. I'm presenting two different cross-sections. While he's measuring the same cross-section with two different algorithms, and the leading order result, where the jets have no properties, they are trivially equal in his case. This is not what applies here. So this is a different thing.
Klaus, you want to ask your question, Klaus?
Yeah, just some comments. So first of all, the problem will not go away if we include next to leading order. Of course, this would be much better. And there are some first results that were presented on NNL 043 jets. I'm not sure whether they are complete. We don't have them at hand. At next to leading order, you would also like to look into the perturbative expansion, because in the end, it comes back to the point that even if you choose different central scales, you would like to have a nice perturbative convergence. And that was, for example, investigated in one of the inclusive jet papers by the NNL jet group. So it would be good to have a look there for different central scale choices, because that is what it in the end comes to. Two different choices, equally, let's say, motivated by physics, but then you have to look into the convergence and choose the one which in the end is better. So the argument here, I think, is not going far enough. We have to look more into the convergence given by them.
I see, but I thought Gavin had proposed let's say a more physical scale, no, for the processes.
Yeah, wait, I was not finished. The merit here is that this would enable you to choose a totally different scale, like, for example, PT3, and look at the convergence, what happens when you really choose the PT that happens at the alpha S order that is not cancelled in the ratio. That is a merit which you could investigate here.
Sorry, Klaus, I'm not sure if I got your point really, right? Whatever you do, whatever scale you choose, right? You can always compute these two things, right? You can always compute it like in the standard approach. You can always do that, and you can always do that. In this case, I've done this at next to leading order to compare to what we have. This can be done at any order, right?
No, you can't.
And for every
because if you choose PT3, in some cases you don't have a third jet, so you don't have a third jet PT if you take it in the numerator and denominator separately. However, if you look into the ratio in your expansion, then you always have something from third jet components. So there you can choose PT3 as a scale, not in the standard method.
I think that the issue is not that much what is the scale, but where do we evaluate alpha S at the end? Because this is a problem with different scales. So, and we are extracting alpha S, we are extracting alpha S at which PT, PT1, PT2, PT3. So that's the issue that, but I thought this had been solved, no? Maybe I'm wrong.
A comment here?
Yeah, a brief one, and maybe if it goes on longer, we should take it to the discussion session.
Yes.
I'm just saying that this looks like looking at the theory uncertainty in a different way from scale uncertainty, but it's very like correlated because you're looking at the next higher order term that you don't know and vary it in some way, which is the same, but that you, well, similar to doing the scale variation, but the logarithmic terms give you an estimate of the missing higher order. So, I mean, it could also lead to some kind of double counting if you take both.
Okay, so maybe we can really take it to the discussion session. And we move now to the next talk by Bogdan. Go ahead, Bogdan.
Okay, so first, thanks to the organizers for giving me the chance to say a few words on this topic, which has to do with the energy range for the RG test and the PDF sensitivity in alpha S evaluation from jet cross-section ratios at the LHC. You may note that the first point here has to do with what David has just mentioned. And David, as you will see now, maybe this is not yet completely solved. I mean, let's see that. So it's based on some thoughts on that I presented at a workshop a few years ago, and also on this recent paper with Thomas. So let me, okay. So in this talk, I will show a few examples of measurements of cross-section ratios. So R32, R delta phi, and also this energy-energy correlation measurement. And I will not go into all the experimental details, but rather use this as support in order to discuss these two topics. The first one being this energy scale that is relevant for the RGE test, and the second one being the PDF sensitivity. And by PDF sensitivity, I mean both for these observables themselves and also in the extraction of alpha strong. It happens that these observables are generally presented as observables where PDF sensitivity disappears essentially, or is strongly reduced, just because one takes a ratio and the PDFs are involved both in the numerator and the denominator. This is an argument that you can see in many papers and many talks, and I think we've heard it earlier at this conference. So let's look at the numbers and see how this looks like in practice. Okay, so I will start with a relatively old measurement, again, just as an example, a measurement from Atlas. I will show later also some results from CMS. So just to set the stage, I consider here this measurement of two quantities. First, R32. So this is a 3-jet to 2-jet cross-section ratio, where there is essentially one entry per event filled at the PT of the leading jet. So you have here the measured quantity as a function of the PT of the leading jet compared with theoretical predictions for two different alpha S values, which shows that this cross-section is indeed, this cross-section ratio is indeed sensitive to alpha S. And you have a second quantity called N32, where the difference is that there is one entry field for each jet. So the same kind of 3-jet to 2-jet ratio, but with one entry per jet. Here also you see the measurement, you see the two predictions for two different alpha S values, and you see that this one also has even stronger sensitivity to alpha strong. Now, there were some studies done into some detail for what concerns the scale choices and the scale uncertainties into these measurements. For example, there were this kind of 2D scan as a function of the renormalization and factorization scale, both for the absolute cross-section and also for the ratios that you can see here at the bottom. The scale choice used here was the PT of the leading jet for the R32 observable. In the case of N32, it was the PT of each jet. And this was treated, the scales were treated as correlated between the numerator and the denominator. And this comes back to the remark from Julia earlier, which I think is very relevant, namely that the question of the evaluation of the scale, or actually what we mean by this is the missing higher order uncertainties for ratio observables, should be treated with some care in terms of correlations and possible cancellations in these ratios. Okay, then what you can see here are again the scale dependencies in terms of variations of the renormalization and factorization scale. You see here the standard variations by a factor of 2 with all combinations of variations of the two scales, except the one going in opposite directions, which would yield large logarithms. So if you compare these two plots for R32 and for N32, you can see that actually N32 is less sensitive to the scale choice, and we saw earlier that it also has better sensitivity to alpha s. Therefore, this is what was used to extract the final result. And all this was done in this study with this jet size of R equals 0.6. So now the extraction itself was done with a chi-square fit, and the chi-square by degrees of freedom can be seen or interpreted in terms of a test of the renormalization group equation. This fit here, or the chi-square of this fit, takes into account the experimental uncertainties and the correlations. The theoretical uncertainties are propagated through plus or minus 1 sigma shifts in order to avoid constraining this theory. Therefore, maybe this chi-square is a little bit too pessimistic. Here, this result, as you can see in this plot and also in the numbers here, was actually at the time a 10LO dominated by scale uncertainties. Now, to get to one of the points of this talk, it's interesting to also look at the results obtained with different PDF sets as listed here in this table, and to look at how much the nominal result changes when looking at the different PDFs. And you can see that the variations when changing the PDF set are of the same order of magnitude as actually the experimental uncertainties. And I'll get back to this later. Switching now to a different observable, the R delta phi that Markus has just presented before. So just a brief reminder, in this observable, one has a ratio in the denominator, an inclusive cross-section, and in the numerator, a delta phi cut for the dijet system, requiring the jets not to be back-to-back. So you can see that this is actually measured here as a function of three quantities, namely HT, Y star, and delta phi max. And the scale that was used here is HT over 2. So what makes this quantity, this ratio here, non-trivial? This is precisely the emission of one extra jet, a third jet, which prevents the two leading jets from being back-to-back. So these event topologies are the ones making this quantity non-trivial. This is what yields the sensitivity to alpha strong. And therefore, I think that the scale at which one probes actually alpha strong, and therefore the renormalization group equation here, has to do with the third jet mainly. So let's look also into the extracted numbers from these measurements. So we have here with a table of alpha S as various energy scales, and you can see in this table also the PDF uncertainty is extracted from the MMHT eigenvectors, and also the variations when changing among various PDF sets. So you see this for every energy bin, and here at the bottom you see the same kind of table now combined among the various bins, so for the full range. And if you look at the numbers, here you can see that, okay, the MMHT eigenvectors yield an uncertainty somewhat smaller than the experimental one, but at the same time, the PDF variations yield a number at least of the same order of magnitude as the experimental one. So here, again, in some sense, one sees this PDF sensitivity. Finally, the last result I wanted to show from the Atlas side is from energy-energy correlation. So here again, I don't go into details with respect to the selections. In all the measurements I've said, essentially central jets are used, and with some PT cut. So this observable here is essentially an energy-weighted angular distribution with the weights proportional to the energies, transverse energies of the jets. So in an event, one takes all the pairs of jets and fills one entry for each of them as a function of this cos phi variable. So now, what is interesting to note here is that from the point of view of the theoretical calculation, this quantity is also computed as a 3/2 cross-section ratio. Here also, exactly as explained before, the non-trivial aspect of this quantity originates from the probability of emitting this third jet. I also list here the renormalization and factorization scales that have been used in this theoretical prediction. In particular, for the renormalization scale, this is HT2 over 2. So now this measurement also has sensitivity to alpha S. Okay, what I found available publicly was this plot from 7 TeV, but at 8 TeV it works the same way. So you have here theoretical predictions for different alpha S values for both this transverse energy correlation, and also I should have said for the asymmetry. So the asymmetry of this quantity, the one where one takes the entries for an angle phi and for pi minus phi and takes the difference between the two. So both of these two quantities have sensitivity to alpha strong, and then a fit is performed through a chi-square minimization, taking into account the correlations of the experimental uncertainties, and the good fit quality is interpreted as a test of the renormalization group equation. Here also the theory uncertainties are propagated through these plus or minus 1 sigma shifts as discussed just before. So now going to the tables of results. So you can see here a first table with alpha S values extracted at the scale that was considered in the theoretical calculation, namely this HT2 over 2 scale used for the mu r. So you see the running of alpha S, you see how the values decrease with the energy scale, and then you also can look at the various contributions to the uncertainties, in particular the ones from PDF. And at the time with NLO, the scale uncertainties were still dominating. Now, I've already made this remark before. For the various cross-section ratios, the sensitivity to alpha S originates from the probability of emitting a third jet or a higher order jet. And actually, in this 8TV publication from Atlas, this effect was acknowledged in some sense, in that sense that these values from this scale here, they were taken and evolved to the average PT of the third jet. So, okay, of course, one goes towards the lower PT, the alpha S value obtained is larger here, but what's more important to notice is that this average PT3 is significantly lower than the average HT2, by definition in some sense, but also from the topology of the events that are being selected here. So this doesn't fix the issue, but at least brings up the fact that this may be a scale that has more to do with the scale where we have tested the normalization group equation. And similarly, afterwards, for the asymmetry, you have the same kind of tables, and for the same reasons, both types of results have been presented. So to summarize on this first topic, I show again this plot that you've already seen in the talk by Markus. So you have here a series of measurements, and I try to indicate here the scales that have been used for a few of these measurements. For R delta phi, so you have the HT over 2. For the energy correlation from Atlas and the CMS R32 result, there's this HT2 over 2. And then for inclusive jets from CMS, there's PT jet, and from the 3 jet mass, there's the 3 jet mass over 2. And now the question that I have here with many question marks is, can one really claim the test of the renormalization equation at scales that are derived from event level observables, like you have seen in all the examples before, either the PT of the leading jet or the PT of all the jets, or the HT2 or HT2 over 2. I mean, and in particular, I would focus also on this quantity, which is the tri-jet mass over 2, which can be large even for low PT values. If you have 2 jets in the forward region back to back, this mass value can get very large. So I think this is a real question. The traditional criteria arguments used to, like, for example, minimizing the scale uncertainties or the K factors are not relevant, I think, for this discussion here about the scale at which the RG is being probed. And I think this scale actually has to do more with the PT of the third jet, and as we've seen before, this is quite low compared to the scales that are shown here. So if this was modified, actually the picture we have from this kind of summary plot would change quite a lot. Many of the points you see here would be shifted to much lower scale. In order to be able to do that, of course, we need consistency between the scale of the theory calculation and the claim we make at the end about the scale at which we have probed the RGE. And this still has to be done. This issue is not solved, otherwise this plot would look completely differently. And I think here the mean law procedure may provide a way forward. So I'm switching now to the second topic again, the one with the PDF sensitivity. So going back to this transverse energy correlation and the asymmetry, I show here the alpha S results at the Z scale obtained from the 2 observables for various different PDF sets. So if you look here, there's a column corresponding to the PDF uncertainties. These are the uncertainties coming from the eigenvectors or the replicas in the case of N and PDFs. And you can notice here also that they are somewhere in between the experimental uncertainties and the scale uncertainties. The same, maybe here, okay, for some PDFs they are a little bit smaller in the case of the asymmetry, but still for any PDF, the most conservative result. So this PDF uncertainty is somewhere in between the experimental and the scale. And now if you also look at the variations when changing the nominal PDFs, these are also quite significant. So the thing to note here is that once again the PDF uncertainties cannot be considered as being negligible. I have one slide with 3 sets of results from CMS. So from the R32 at 70 eV here, you see a similar conclusion with the PDF uncertainty from eigenvectors between the experimental and the theory. Similarly, for what concerns the PDF variations, they are not negligible at all. Then R32 at 8 eV, interestingly enough, so here you have the results from the cross-section ratio itself, but in addition, CMS also extracted alpha S from a joint fit of the 2-jet and the 3-jet cross-section ratios, as you can see here. And if you look at the uncertainties of these extractions, they are not so different. And also, if you look at how much the central value changes when the PDF changes, they are quite similar between the case of the ratio and the case of the absolute cross-section. Even in the case of the ratio, there is one variation here that seems to indicate that R32 is more sensitive than the cross sections. I mean, the extraction of alpha S from R32 is more sensitive. And if you look at the combined result, similarly, I mean, the PDF uncertainty is between the experimental and the scale ones. And now I've also shown here the 3-jet mass. So this is not a cross section, but just to fix the orders of magnitude. So from this absolute cross-section, you have an extraction, and you see here again that the PDF uncertainties for alpha S are between the experimental ones and the scale uncertainties, closer to the experimental ones, which are smaller. So all this to say that when you compare here absolute extractions of alpha S from absolute cross-sections or extractions from ratios, the picture from the point of view of the PDF sensitivity is not so different. So why is that? I mean, one would expect, as I said at the beginning, when taking a ratio, you see this in papers, the PDF sensitivity should be strongly reduced. So this is what I'm trying to explain here, showing just some Feynman diagrams that are involved into the calculations of these processes. So again, remember, what makes these quantities non-trivial is the probability of emitting some extra radiation. So if you don't have this extra gluon here, this ratio here is just trivial, and similarly here. Now what happens is that one has several Feynman diagrams that can produce the same final states, of course. It's just that the probability of emitting one extra gluon in the final state does depend on whether one has a quark line here or a gluon. For obvious reasons, but through the matrix elements that are involved here, actually, the final state particles are, of course, correlated with the initial state ones, therefore with the PDFs. So I think fundamentally this is why we see that in the end, okay, one has some reduction of the PDF sensitivity, but it is not that large because the matrix element correlates the probability of having this extra radiation with the partons that are involved in the initial state. And now another remark that I want to make is that when taking a ratio, it's true that one reduces a little bit the PDF sensitivity of the observable, but one also reduces the sensitivity to alpha S. And this is what you have seen into detail in the talk by Markus just before. And basically, there's a competition between two effects when asking the question, what will be the final PDF uncertainty for an alpha S extraction? It's true that this observable reduces the PDF sensitivity, but it also reduces the sensitivity to alpha S. So in some cases, it's one of the effects that wins. In some cases, is the other, as you have seen in the previous examples. And okay, I will stop here. Thank you very much.
Thank you very much, Bogdan, for this interesting presentation. I see already one hand. No, sorry. sorry. Marcella?
Yes, thanks, Bogdan. Can you go to slide 13? But I agree that, right, in a multi-scale problem, it's not so trivial to select the scale at which you're going to quote your alpha S value. Now, I don't quite understand why minimizing the uncertainty or looking at the convergence of the perturbative series isn't the guidance there, right? If my observable is based on the PT of the third jet, and that drives my alpha S sensitivity, shouldn't I get the best convergence for the right scale, just like in any other case?
It is, I think it is a little bit more complicated than that, because as we have seen in many examples, I mean, the scale variations provide some information about the missing higher orders, but it is not just as simple as that. We have seen many examples where actually a scale variation at NLO, for example, doesn't cover at all the difference with respect to N2LO for good and well understood reasons. And in particular, there are new kind of diagrams involved at higher orders. So I think this criteria really cannot be used here in the discussion about the scale at which the measurement is really sensitive to. I think in some sense this is independent of the theory calculation, if you wish.
I think it remains a tricky game, but I don't see your argument, to be honest. Can you elaborate a bit more on this min-low procedure that you proposed to?
Oh, I mean, there are experts in the room who know this much better than me, but the basic idea, as I understand it, is that this procedure takes into account when looking at the Feynman diagrams, the fact that different scales are involved when looking at different parts of that diagram. And I think this is really the key here, because what makes these observables non-trivial is really the probability of emitting this extra radiation, like a third jet, etc. So I think somehow we need to be able to access the scale at which that emission takes place.
Yeah, I think that makes sense. If this gives us a procedure to identify at least the consensuated scale by the community more clearly, that would be a step forward, I think. Thanks.
Okay, thank you. Matt, do you have a question?
Yes, I do. It's about a different topic, though. If Klaus wanted to reply here, maybe he should go first.
Sorry?
Well, yeah, okay. So there are 2 points which are, let's say, criticized here. One is the central scale choice in general, but everybody knows that scale variations are just, let's say, a poor man's proxy for knowing what the higher order impacts are. So I'm not sure why, for example, you're quoting here the CMS 3-jet mass. This is an absolute cross-section, has nothing to do with the other problematic of normalizing or ratios. And from Daniel's presentation, we have seen that in particular for the dijet mass, it's a recommendation from the NLO jet people who have did a long investigation on the convergence of this series to use the dijet mass for this scale. So I don't know why this is here criticized. Huh? And then for the ratios, of course, there are different scale choices, you know this. But if you look, for example, the CMS result, the dominated uncertainty is still the scale uncertainty that's plus minus 50. It's far beyond anything from the experimental or PDF uncertainty. So I really don't understand what you make as a point here.
So let me clarify, Klaus, maybe. So for the 3-jet mass, what I criticize is not the scale that is being used in the calculation. I'm aware of the convergence properties and all this that has been studied into detail by the people who did the N2LO calculation. This is not the point. I mean, the point is about where the sensitivity comes from. And I think this is very sensitive to the diagram that you are looking at, whether you consider the S channel or the T channel diagram. And what I was trying to point to is that even for this observable, if you consider 2 jets in the very forward region, so with a small exchange in the T channel, then one can wonder if really one has probed the RGE at this high scale. This is what I'm questioning. It's not the scale used in the theoretical calculation, if you wish, but it's again, what I'm discussing here has to do just with the scale at which the RGE was probed. It's just
okay. So Bogdan, let's concentrate on this here. For sure, if you take if you do comparison of a measurement and the scale that you choose has nothing to do with the observable, then probably you will see that your prediction and the behavior of the prediction do not very well match the data. Here in this particular case, one must add to this observable that the rapidity is constrained, if I remember correctly, to plus minus 2 something. Yeah, so you don't have the possibility of having forward and backward jets in the observable like it was investigated in the CMS analysis. If I would take forward backward jets at plus minus 4 or so and then use this scale, probably I would see that it wouldn't work to describe the data.
Right, but plus or minus 2 something is already I mean, relative forward, I would say. But
I'm sorry to cut this discussion, but maybe we should really move it again to later on. Klaus, would you agree, Bogdan?
Yeah, I'm fine.
We were a little bit running again, a little bit late. There is one more question, maybe a quick question, and then we move to the next talk.
Yeah, I think this is a quick question, Bogdan. I thought your points on slide 16, where you were talking about sensitivity of these measurements to PDF fits, were interesting. And this is something I was actually just talking about very recently with someone else. So my question is, when measurements are being done of cross-section ratios, would it make sense also to publish the numerator and denominator separately as an additional input for PDF fitting and things like this? Or you know, is there some way that these publications could provide information in a more convenient or a better form for PDF fitting?
Okay, I'm not so much a PDF fitter myself, but I think it provides PDF sensitivity. Therefore, I think it will be valuable information. And as you have seen, I've just cited one measurement from CMS earlier where this was actually done. So I think it is valuable information. Now, I'm not aware if someone has actually tried to use this in a full combined PDF fit, but it would definitely be interesting.
Okay, cool. Thank you.
Okay, thanks. Wonderful. Please go ahead, Stefano.
Thanks. Okay, so I would like to report a little bit on some studies on measuring alpha S from the Z-boson transfer momentum distribution. So first of all, since this is a kind of new observable for the measurement of alpha S, I would like to recall what are the desirable features for an observable. So first of all, we would like to have a large experimental sensitivity to alpha S, then as much as possible high accuracy of the theory prediction, and the third important point is a small size of perturbative QCD effects. So a little bit of history about a class of observables that are called semi-inclusive, that means radiation inhibited. So there is actually a paper about 30 years ago, a quite famous paper from Catani, Marchesini, Weber, that for the first time proposed to measure lambda ms bar from semi-inclusive Drellian cross-section. In that case, they were considering rapidity, so it was not exactly the same observable, but in a sense, they were already envisioning this kind of observables. So here, the specific semi-inclusive observable that I am considering is the ZPT distribution in the Sudakov regions. So here I show as example a recent CMS measurement where we can see very clearly this Sudakov region where we have a nice peak at about 4 GB. So what characterizes semi-inclusive observables? So if we think about fully inclusive observables, the benefit here is that we can usually have higher order theory accuracy and smaller non-perturbative QCD effects, but in general, we also have smaller experimental sensitivity. On the other hand, we have exclusive observables where the experimental sensitivity can be much higher, but in general, it's much more difficult to have high order prediction, and we can have easily larger theory uncertainties. So semi-exclusive plays an interesting role because we are, in a sense, in the middle, and we may take benefits from both categories. So in particular, concerning the Z-boson PT distribution, we have experimentally an extremely clean final state. So we're measuring two leptons, which are very well calibrated, for example, in alpha and CMS, but also at the temperature, it was the case. We have very little background, and we have high experimental resolution. So we can really get very high experimental sensitivity on alpha S and Z. Here I'm showing an example of the latest atlas measurement, and if you look at the total uncertainty for this measurement, we are at the 1 or 2 per mille level in the Sutakope region. From the side of theoretical predictions, there has been quite a lot of improvements in recent years, and the standard is now N3 LL prime resolution supplemented by N3 LO virtual corrections and matching. So here I show a few examples of recent calculations. So concerning the experimental data that I've chosen to work with, this is the CIDF measurement of Z-boson PT distribution in full lepton phase space. This is a very good candidate for forced determination of alpha S and Z with this technology. The first reason is that the measurement is extrapolated to full lepton phase space. So this is still currently the only measurement of this kind. And the extrapolation is done with the angular coefficient method that is quite a nice method because it allows an extrapolation that basically has little theoretical uncertainty because it relies on the analytic continuation on some spherical harmonics. The technical advantage is that we can work in full phase space with fast analytic predictions, and we also avoid theoretical uncertainty on Z polarization and also on linear power correction related to lepton cuts. These are usually not very large, but it's still an interesting advantage. The other advantage of working with Tevatron data is that we are in ppbar collision, and here an important point, we have a much reduced contribution from a flavor initiated process compared to the LHC. So to give some numbers, at Tevatron energies in ppbar collision, we expect dV-bar contribution below 0.5% and CC-bar a little bit above 1%. So this is also a nice simplification of the analysis, and because we don't need to worry very much about any flavor initiated contribution and related uncertainties. Interesting feature of the CDF measurement, this is done in the electron channel, so the CDF coverage in the forward calorimeter is up to eta 2.8. This is very close to the kinematic limit of Z production at the Tevatron, 3.1 rapidity, and that means that the measurement is actually even extrapolated to full rapidity range with really a very small extrapolation, so no large inclusion of PDF uncertainties because of this. Also, this was low pileup data. These are the first two inverse femtobarn of Tevatron data. To give some numbers about resolution, in the central CDF calorimeter, we have 0.9 GeV resolution, and in the forward, we have 1.1 at the energy relevant for the Z-boson. And so, as a consequence of this relatively good resolution, the measurement is done in fine beams, 0.5 GeV with small peer-to-peer correlation, which is also an asset for this measurement. So concerning theory predictions that are a crucial ingredient for this analysis, I used DY Turbo. This is a public code that is based on Catani, De Florian-Grazzini QT resolution in this space. So basically there are two pieces for the calculation, a result prediction and a matching to fixed order. If we look into the result prediction, the two important pieces that are relevant here are the R coefficient that is evaluated at N3 LO accuracy and the pseudo-buffer factor that is evaluated at N3 LL. In this particular analysis, the matching is done at one order less, so at next to next leading order accuracy. However, as it is shown in this plot, it is showing the finite order contribution. We are talking about the missing correction order alpha SQ that is at the level of per mille or even super mille in the region that we are interested in, that is below 30 GeV. So in summary, I mean, except for this little missing piece, we have a consistent N3 LO calculation where alpha S is running at for loop in all parts of the calculation. Actually, this alpha S running at for loop is done also in the PDF evolution that are evaluated in the Catani, De Florian-Grazzini at the hard scale and evolved with a fixed flavor number scheme at 5 flavor. Finally, what I've used for the non-perturbative effects is a relatively simple model, but we will see that works very well. That is a simple Gaussian pseudo-comfort factor that is governed by basically by the width of the Gaussian in this space that is a parameter G. So let's now understand a little bit the sensitivity to alpha S. So the left plot is showing the effect of large variation of alpha S on the ZPT distribution. You see that larger alpha S means a shift in the position of pseudo-curve peak. The typical scale of this recoil is, yeah, we can think about it as the bicentrum of distribution, that is about 10 GeV. And on the right, I also show the sensitivity to the non-perturbative Gaussian form factor, because this is a quite important source of uncertainty. And you see that the interesting feature when we do variation of the G parameter is that the region of the PT distribution that is affected by this lives at smaller values of PT. And the reason is quite natural, because while the typical recoil scale of the perturbative pseudo-curve is 10 GeV, the scale of a non-perturbative pseudo-curve is at the level of the primordial KT, that is about 1.5 GeV. So this simple observation is the reason why we can actually disentangle in the same fit alpha S and G. Concerning the methodology for the alpha S and Z determination, I've used X-fitter, so I interface this Dugo-Turbo calculation to X-fitter. The alpha S variations are provided in LHC-PDF, and the PDF uncertainties are included in the chi-square with this, well, with the standard X-fitter formalism with these beta terms. That means basically that at each value of alpha S, we are profiling the PDF. So this is the usual inclusion of additional data without refitting. Technically, the non-perturbative form factor is added as an unconstrained nuisance parameter, so we set beta equal 0 in the penalty. So it's basically an effective way of getting the non-perturbative form factor to be free in the fit. And as I already mentioned, the fit region would be ZPT less than 30 GeV. An important correction that needs to be added is QED initial state radiations, because Dugo-Turbo is not yet able to do it. So I've used an external beam-to-beam correction from Pizia. You can see here the effect of this correction, which is rather small at the level of 1%, and the estimated effect on alpha S will be delta alpha S 0.0004. It would be nicer, of course, to have QED included in the QT resummation formalism, as was shown in this paper. However, you see that Pizia is not actually very far from what is predicted from combining the QCD QED resummation. And since this is a small correction, the associated uncertainty is expected to be smaller and actually neglected. And now let's come to the fit results. So here you can see the result of the post-fit comparison of prediction to data. Here in this example, I'm using NNPDF 4.0. So the central value of alpha S is 0.1187. Here I show the breakdown of the uncertainty in the fit. So we have 0.7 10 to the minus 3 contribution from the statistical uncertainty, 0.2 10 to the minus 3 from the systematics, and 0.4 is the estimated NNPDF 4.0 uncertainty. The fit is also yielding a value of G that is 0.66 GD square with an uncertainty of 0.05. By repeating the fit with different PDF uncertainties, we get a spread in alpha S that is plus 0.6 minus 0.9, 10 to the minus 3. So what is interesting to look in this list of PDFs is that I have included CT18Z. This is a different instance of CT18, which include large stranges, but most importantly, some kind of limiting of small x resummation. So I was particularly worried about possible effect of small x resummation, particularly of gluon shape. And another interesting observation is that ADMP16 is actually a PDF strictly in 5 flavor that is fully consistent with the 5 flavor evolution that is used in formalism of Catani de Florian Grassini. And so basically in practice, these two choices are the largest spread on the envelope. Concerning QCD scale variations, these predictions relies on 3 QCD scales: renormalization, factorization, and resummation. So this particular type of resummation has basically all scales living at near MZ, near the alt scales. So to compute missing higher order uncertainties, I combined all possible choices of scales and neglecting discarding factor of 4. And here you can see the full list of PDF variation of scale variations that leads to an envelope in alpha S of 0.7, 10 to the minus 3, to 1 in 10 to the minus 3. What is interesting to notice here is that the largest spreads comes from configuration where the resummation scale is larger from the renormalization scale. This is can be considered a little bit unphysical to set the resummation scale larger than the renormalization scale, and basically what I think here is that keeping this in is still slightly conservative with respect to scale variation, and I think it's fine in any case to have a concerning other Fourier uncertainties, one important uncertainty is related to the particular choice of a non-perturbative effects. In order to investigate these, I perform variation of the Landau and B prescription for avoiding the Landau pole. So the nominal value of B max is 3, so I vary it down to 2, and I also vary it to infinity using the minimal prescription. This gives a large, a spread on alpha S from plus 0.6 to minus 0.4, and variation in delta chi-square, which are at the level of 2. So that means that these variations are fine, a little bit on the conservative side compared to what the data is saying. Another uncertainty that I'm considering is a variable flavor evolution in the PDF, and this gives a small effect at the level of 0.2 10 to the minus 3, and the reason is because we have very little contribution of very flavor in production in this data. Finally, I wanted to check the stability with respect to the fit range. So I vary the fit range from 20 to 40. You see that there is a very, very good stability of the fit. By reducing or enlarging fit range, we have a small change in the fit uncertainty. That means that really the sensitivity to alpha S is coming from the peak and doesn't really matter very much where we put the fit boundary. This is nice, and also confirms the fact that the missing or the alpha S cube terms in the matching have basically a negligible effect. So coming to the result. Summing up all uncertainties, the measured value of alpha S is 0.1187 using an PDF 4.0, but an envelope of PDFs for determining the uncertainties, and plus 1.3 10 to the minus 3 minus 1.6 10 to the minus 3 is the uncertainty. And here I repeat again the breakdown of the uncertainties that I described before. This is basically in agreement with the world average, and the uncertainty is comparable to other determination as it is summarized in this plot. So to summarize, this is a preliminary measurement of alpha S using an observable, the ZPT distribution in the Sudakov prism, and using the CDF data. The result is 0.1187 with a little bit more than a 1% uncertainty. The determination is performed consistently at end-free LO, and I would say that the characteristic scale of a measurement is related to the average value of PT, of the Z-boson transfer momentum, that is something at the level of 10 GP. This measurement is based on a semi-inclusive observable. I think this is maybe the first time in hadron colliders. It has different features than other inclusive or exclusive observables, so it's, I think, an interesting thing to explore. Another consideration is that this particular observable, the low ZPT distribution, is not included in an PDF fit. There is, I think, no reason to do so, because it has more sensitivity to collinear PDFs, and it's also obviously not predictable in fixed order perturbative QCD. So I don't think this particular measurement should go in the same, exactly in the same categories of alpha S extracted from PDF fit, but of course, I mean, this is maybe just a matter of categorization. I use a conservative approach for PDF uncertainties, including an envelope of 6 different PDF sets, and in particular, what I found important to be conservative is to include CT18Z and ABNP, because they really include some kind of different physics that is relevant for this measurement. The non-perturbative QCD model is based on a Gaussian form factor. This is simple but very effective, because the agreement with the data with the simple model is already extremely good. I mean, in order to assess uncertainty, in addition to having the parameter free, that of course is an inflation of the uncertainty of the fit, I treated differently the Landau-Paul prescription that should be relatively conservative with respect to a simple choice of a non-perturbative model. So since this was somehow requested by the organizers, I also tried to write down a wish list for future measurements in the next years. So from the experimental side, I would say that the measurement of Z-boson PT are already extremely precise. So if we look a little bit in detail at the uncertainty breakdown, assuming that in future measurement the statistical contribution here shown in blue will go down basically at will with future data. What will be the next dominant uncertainty to address is the lepton, momentum and energy scale. Currently we are at the level of about 10 to the -3 in the experiment, and it's probably possible to bring this down even at the level of 10 to the -4, and this is will in any case be beneficial for the measurement. Other interesting things will be to measure, well, it's already measured, but let's see, to have better precision on PT of the Drellian at high mass, because this will give further sensitivity to alpha S with even smaller sensitivity to the non-perturbative QCD, and also precise measurement at low PT and the low intermediate mass will help to fit and reduce the non-perturbative uncertainties. For the theory wish list, I would say that, and for LL, ingredients are of course very welcome. But part of this is already there. It's also Sven provided an approximate 5-loop cusp estimate for the cusp anomaly dimension. Other things are probably coming very soon, and for LL prime I think is quite far in the future yet. There are some of these missing pieces that are probably very difficult to derive. Other things that will of course benefit the measurement, in particular to be able to do this at LHC, are improved heavy flavor treatment, joint QT small X summation. There are already results on these, but not phenomenological studies. QD, QCD is probably already there, just needs to be included. And something very important will be some additional first principle understanding of non-perturbative corrections. I've seen that in the case of the plus minus, there are a lot of interesting works. Maybe this can also be done for Drellian. Thanks. This is basically all that I wanted to say.
Wonderful. Thank you, Stefano, for this interesting presentation. We have a question by Mandy. I think so. Mandy, you're muted. Okay, then maybe Simone can. Okay.
Sorry, I got unmuted. Sorry.
Okay.
Yeah, thanks for a very interesting talk. You were talking about scale dependence, and you added the scale for resummation to the usual factorization and the renormalization scales. I didn't get in your talk where the resummation scale had come in the calculations that you're making for this.
Yes, so sorry, I didn't give many details on the theory formalism, as it's not exactly. I mean, I didn't give many details, but basically the resummation scales enter mostly in the pseudo-comfort factor. So here I didn't put the details, but G depends on mu R and also the resummation scale.
Yeah. Okay, thank you. That's just what I wanted to know.
Simone?
Ciao Stefano, very interesting result. I have two questions. So the first one is, if you have studied or you have looked at the dependence of the alpha S extracted on the model you assume for the non-perturbative form factor, if you have tried anything beyond the simple Gaussian.
Yes, yes. So there are authors that basically suggest that in the very large B region, one should have an exponential for factor. There are even fits that try to do this and say that this is equivalent. What I found in this particular fit is that an exponential for factor alone is completely off, completely excluded from the data. These for sure must be related to the nature of power corrections. So I think I mean, there were studies of this in the past, and also at the level of BL and Y. So there are reasons why CSS suggested Gaussian for factor many years ago. So I think this is probably a known thing. I also tried another kind of Gaussian for factor proposed by Collins and Roger, and this is also very off from the data. It's basically impossible. I mean, I think the Gaussian is a simple model, so it can have some drawbacks. For sure, what TMD people are doing is much more sophisticated. However, we should keep in mind that when we fit the ZPT, we are at such a large, this is most visible here. We are at such a large scale that basically whatever we do in the non-perturbative region is basically just in the few 2, 3, maximum 4 beams of distribution. The LHC would be basically 1 beam from 0 to 2 dB. So it's even very difficult to say let's plug in a different model and see something. For that, one should really look at low mass Stratian as a function of PT, and there's some first principle understanding or more sophisticated fields. But I think the key point here is that the alpha S extraction is relatively insensitive to these details, I would say.
Thanks, yes, this I think is what I was after. So the second point is about possible LHC extractions. And basically, if you could comment on the heavy flavors. So if you think there's any avenue to somehow get anything better than a massless calculation for the LHC. I mean, I've seen that for fixed order, there are sort of variable flavor numbers scheme merging of massless and massive calculations. I haven't heard anything for resummation.
Yes, no, there is an old paper by Nadolski and collaborator Fred Olmes, also was there, that was basically looking at massive correction in the ACOT scheme at the Tevatron. There is quite nice work by Skett, Frank Tuckman, and Davers that was, I think, really calculating all the ingredients for doing this in Skett, but no phenomenological study. There was also a proposal by Mito and others on a practical implementation of massive and massless variable flavor number scheme for general processes. So I think many things are already there. What one needs is really to see an application to this particular observable, I think.
Thank you.
Okay, thank you. We take a question here from Pierre.
Thanks. Hi, Stefano. Just a quick curiosity. Have you tried to vary the fit range from below and reduce the impact of non-perturbative corrections?
No, I didn't try. This is an interesting point. The reason I was not very happy about this is because I am a little bit afraid about the overall normalization. So probably in the Tevatron case, it's still fine because there is a large 6% luminosity uncertainty, but I would be a little bit worried of doing this at the LHC because at the LHC, the luminosity uncertainty is at the level of 1.5, 2%. And so removing a region of a spectrum where we have a large luminosity, I was afraid that basically forced myself really to work on absolute perception with maybe some issues. But yeah, I think it's a nice suggestion, so it's something that should be tried.
Okay, thank you. David?
Yes, thank you, Stefano. Very interesting. Again, I'm maybe it's part of the issues that have been raised already, but I was wondering about the non-perturbative part. To what extent, when you fit both alpha S and the G factor, you are not putting some uncertainties from alpha S under the rag of the G parameter? So, are you really sure that that you control that you properly propagate the non-perturbative uncertainties properly to the final alpha S uncertainty?
Yes. So in this respect, I think that the safest thing is what I'm doing, but is fitting both parameters together. maybe what can be improved, I think this is a nice suggestion, is the practical methodology. So right now, G is fitted basically with a 2-point or 1-point, 2-point quadratic approximation of 1-point linear approximation. One could do a real minimization of the non-perturbative parameter with each alpha value. That would be, I mean, from a technical point of view, of course, more stable, but it should lead basically to the same result. I mean, here you don't see explicitly the G uncertainty because G is a free parameter. But if I fix G, basically all uncertainty gets divided by 2. That means that there is still basically something at the level of 50% correlation between G and alpha S. So G is really limiting the alpha S precision.
Okay, and then the last question rapidly about the LHC, to what extent, because the nice thing of this is that the CDF, as you said, PT differential spectrum is not part of the global fit, but as soon as you include now ATLAS and CMS data or LHCb data, those data are in principle part of the global fit. So aren't you
above 20 or 30 GV, not in this region?
Is that correct? I'm not sure.
I'm sure about it.
But we had a discussion 2 days ago about whether the total inclusive W and C were part of the global fits.
Yeah, right. So what I could do is just leave the normalization free. That is basically fit basically 1 sigma, the sigma of the T. So we remove the information from the inclusive cross-section. That would basically change nothing.
No, what I think is, I don't know, maybe the PDF experts can comment. I think the worry is that whether you will be somehow double counting, because if this data is already included into the...
But the ZPT in the pseudo-cov region is not included. It cannot be included in a PDF fit with current technology.
Well, that this was the claim that yesterday, that, I mean, of course, this region is what dominates the total cross-section, total inclusive cross-section. So in my alpha S extraction using the total cross-section, some of the PDF fitters were claiming that part of this data is already there. So there is a contradiction between what I say and what they say. What they say and what you say, sorry.
No, so there are two different, okay, let me answer better. So there are two different things. Some fit NNPDF, for example, is using the ZPT distribution above, I think, 20 or even 25 GV, using a Z plus jet next to leading or next to reading order calculation. And there was a nice study by Maria Ubiali et al. A long time ago about measuring alpha S from these, and this was included. But this is basically no or marginal overlap with the pseudo-cov region. I think this is at all not an issue. Then the other thing is that if I use the absolute the sigma DPT cross section, of course, I also have the information about the total Z cross section that may be used in a different form by PDF fits. This is true, but there is a simple solution to that. In my fit I can just fit 1 over sigma the sigma DPT. So I remove completely the dependence of the total cross section. In that case, would be fully orthogonal to what is used currently in PDF fits.
Okay, thank you.
Okay, thank you, Stefano. Very last question by Simone Mazzani. Quick question.
Okay, two quick curiosity. One is whether it would make sense also to look into related variables like pi star, or maybe not, because of the shape you lose a lot of sensitivity to alpha S. And the other quick curiosity was how urgent would be this combined small x and small qt, because this may motivate us.
Thanks, Simone. So maybe we should talk more. So I know your paper, so it's very nice, your paper. I tried to look at it and to use it, but we should talk more. I think for LHC, it's very relevant. So my gut feeling is that at LHC, we are already in the next X range where joint QT small x makes a big difference. So here you see already at the Tevatron, we are talking about 0.5 10⁻³ At LHC, this can be basically a factor of 4 larger, just to give you an idea. So I think it's very urgent and very important. Concerning phi star eta, so phi star eta was a very important variable at D0, because D0 did have a poor lepton resolution, so that was really a game changer to using phi star eta and overcome the problem of not good resolution with DZ. When we moved to the LHC in particular, I checked this explicitly for ATLAS. phi star eta has a very marginal gain in the electron case because the electron does not have as good resolution of the muons. But in the muon case, PTZ is more sensitive to ISR basically than phi star eta. So the difference is very small. And phi star eta is a nice variable, but introduce a lot of complication, technical complication when you fit these, because of course you have to partition the phase space in a completely different way, even possibly resumming phi star eta. So it's a nice thing to look at, but at the LHC it will not be a game changer. Maybe at LHCb, that is a slightly different situation, but at least CMS does not.
Stefano, thank you. We really have to move on now. Sorry.
Yes. Sorry.
Thank you very much. It was very interesting. So now we change topic and we.
Thanks for the invitation to discuss alpha S from tau decays. The formula is well known. We are talking about the weak decay, and therefore the hadronic part is related with the 2-point function of the left-handed current. That means the W self-energy. You just use the optical theorem, so you can see that the R tau, that is the ratio tau going to hadrons versus tau going to electrons, is just given by an integral between 0 and the tau mass square of some weight factors times the spectral functions associated with this 2-point function correlator. Of course, you are not able to predict these spectral functions from QCD because it's in the very low energy region, but you can use the analyticity properties of these correlators. They are well known in the complex plane, and we can rewrite these integrals as contour integrals in the complex plane. So once the experimentalists have measured the spectral functions, the imaginary of pi, any integral of these spectral functions with any weight factors which are analytic between threshold and some S0, which should be always smaller or equal to the tau mass, you can always rewrite it as an integral in the complex plane along the circle S equal S0. That is your maximal, your upper bound in the integral. And of course, once you are in the complex plane, you are away from the real axis where the singularity cut lies. You're away from the physics, and therefore physics is smooth, and you can apply the operator product expansion. It's important to keep in mind that you cannot apply the operator product expansion on the real axis, and I will come to that several times. Well, the formula is well known since 30 years ago. So I have put here a summary of the result, how R tau looks like. Is proportional to the number of colors. There is some electroweak factor that is known at the per mil level. And then you have 1 plus a perturbative corrections plus a non-perturbative correction. The perturbative correction is known to 4th order in perturbation theory. That's impressive. It's thanks to the nice work of the Karlsruhe group. And from experiment, we know that it's a 20% effect. So the strong coupling is large at the tau mass. The perturbative contribution to R tau is very large, so you are extremely sensitive to the strong coupling. At the same time, we also know that the non-perturbative correction is small. I will give arguments in a moment why it is small, but in addition, you can extract it from data. This has been extracted by Clio, by Opal, and by Aleph. And all of them agree that it's below 1%. That is the estimate we did 30 years ago from theoretical arguments. So of course, at the level of precisions that we are talking nowadays, one really needs to be careful and to look into that. One of the reasons why you can do such a precise theoretical prediction is because if you look to the weight factors that happens to be in the R tau distribution, you see this 1 minus x squared, which is just of kinematical origin, phase space. And this kills the region x equal to 1. That means it kills the point where your circle touches the real axis. In this point, you cannot apply the operator product expansion. So in this point is where your uncertainties originate from mainly. But you have a double zero, and that means that numerically, it does not affect your integral. It only starts to affect your integral at about 10 to the minus 4, which is much below the theoretical uncertainties. So let me analyze the separate contributions in detail. So let's start first with the perturbative contribution. So you know 4 orders. So what is computed is the Adler function, these k factors. You plug this into the contour integral, and then you just get integrals of the strong coupling that you can compute numerically, or you can expand. If you compute these integrals numerically, exactly to the order in the beta function that we know nowadays, then you get an expansion in terms of integrals that is called contour-improved perturbation theory. If you decide to expand this in powers of the coupling at the tau mass scale, then you get what is called the fixed order perturbation theory expansion. Okay, so those are 2 different expansions. If you analyze what happens, I have put in the table the original Adler function coefficients and the coefficients you get in fixed order perturbation theory. The difference is what comes from the integrals. And it happens that in the integrals, you have a very long running of alpha s along the circle. So the corrections you get from the integral are much larger than the original contributions of the Adler function. So we don't know the order alpha s to the 5th term in the Adler function, but we do know that the integration is contributing a factor 308, which is very large. Okay, and at this point, you decide which expansion you want to do. These large factors come just from pi squared and pi to the 4 corrections that appear when integrating along the circle. If you analyze this with the beta function expansion, you see that you really control very well these integrals, because you can compute the integrals to 1st order in the beta function, 2nd order, 3rd order, 4th order, 5th order. The convergence is very, very good. I will say it's spectacular. So you really control these functions. On the other side, if you just expand this function in powers of alpha s at the tau mass scale, fixed order perturbation theory, you see that systematically fixed order perturbation theory overestimates these functions by about 11%, which means that once you do a fit to experimental data, you are going to need a strong coupling, which is about 10% smaller than if you use the contour-improved perturbation theories. Okay, so which series you want to use is your decision. People using renormalons like more to do fixed order perturbation theory, because they argue that there are nice cancellations that you miss otherwise. As I see it, in one expansion, you are taking into account corrections that we know they are already there. In the other expansion, you are taking into account corrections that can appear at some order in the perturbation theory, but you don't know exactly where. In any case, I will not enter into this discussion. I'm sure that André Juan will discuss this in full detail, so we can delay the discussion to that talk. So I will be showing results with both choices. The non-perturbative contribution, you just put the operator product expansion in the circle, you integrate, and to the extent that you neglect the logarithmic corrections to the Wilson coefficients, which is a good approximation with the present precisions, then the Cauchy theorem tells you that you just pick up the 1/s singularity. So depending on your wave factor, you pick up one corrections, one other correction. The tau mass scale is small, but at the same time is large enough compared with lambda QCD, which means the first corrections of the operator product expansion have dimension 4, and therefore are suppressed by 4 powers of the tau mass. We know the size of these corrections, so I have put them in terms of the m tau to the 4th scale, so that you see that you get corrections which are below 1%. But in R tau, at least in the distribution that is measured with the tau lifetime, for instance, the power of x does not appear in the weight factor. The first power which appears is x squared, which means that the first non-perturbative correction that you pick up has dimension 6. You get corrections from dimension 6 and dimension 8. You can estimate the size of these corrections by measuring the difference between vector and axial. This is pure non-perturbative correction, okay? And we know it from experiment, and you can easily see that it gives something of order 10 to the minus 4 times m tau to the 6th power. Of course, you can increase the sensitivity to non-perturbative corrections using different weight factors, And that's what the experimentalists did in order to measure the non-perturbative correction, at least to put an upper bound. So just summarizing all these points, you know that there is a QCD correction of the order of 20%. You know that the alpha S is large, so you have a very strong sensitivity to alpha S. N tau is large enough to use the OP. We have a quite flat vector plus axial distribution, is the most inclusive one, and I will show it in a moment. You cannot apply the OP in the real axis, but R tau has two zeros at x equal 1, that is at s equal m tau squared, and therefore numerically you are well protected. And therefore, if you just take the chiral limit, which is a very good approximation, so I neglect very light quark mass corrections, you see that the only non-perturbative corrections which appear are suppressed by at least 6 powers of the tau mass. In addition, this correction of dimension 6, we know from very generic arguments that were already explained by the Russians in the end of the 70s. We know that these contributions have opposite sign for vector and axial, and you expect a cancellation in V plus A. And you can see this cancellation in the data. I think Aleph did a very nice analysis of these observables, measuring the non-perturbative correction. That's what the value Aleph gave to us some years ago. If I just use this value and put it into the tau lifetime without doing any other thing, it's quite trivial. I immediately get alpha S m tau squared 0.331 with a quite a small term. Of course, we want to do better than that. So we want to analyze this error a little. So let me show the second important ingredient. I said the first important ingredient is the calculation by the Karlsruhe group of the order alpha S to the 4 correction. The second one are this collection of refined spectral functions that were updated by the Orsay group with Aleph data in 2014. You can see the spectral function in the vector channel, in the axial channel, and in the vector plus axial. Of course, you see the wiggles of the resonances. They are there. This is the Minkowski axis. There you cannot apply the operator product expansion. But you can also see that once you go to the most inclusive channel, vector plus axial, the wiggles soften quite a bit. So if you are at the tau mass scale, it is about 3 GeV squared, then you are in a quite flat region where you can do many nice tests of QCD. Of course, you can also see here that the 3 large bins have very large uncertainties. This is just because of statistics and phase space. So it will be nice to have better data that improves this part. And in fact, Boito et al. Have tried to use E plus E minus data to improve that. I think they have done a nice work there. So once Aleph measured this, did the refit of these spectral functions, they did a very nice QCD analysis, and they extracted alpha S, but their analysis was quite strongly criticized. I didn't understand why it was so strongly criticized. So we decided to make a complementary analysis, doing a reanalysis of any possible method that had been used until then. So we extracted alpha S using the same RF procedure with these RF moments, the first line, with modified RF moments. You can see the kind of moments that are used in each analysis in the low part of the plot, or using what we call optimal moments, or looking to the S0 dependence, which is more dangerous because you are more subject to duality violations, or even using a Borel transform, that is what the Russians liked more many years ago. And we did, in addition, many other tests of the reliability of the method, how consistent the results were, and how small variations of the assumed inputs were modifying the final results. And our conclusion was that the result was very, very solid. You can see that all the methods give the same results, either using contour-improved perturbation theory or fixed-order perturbation theory. Of course, the largest uncertainty by far is the perturbative uncertainty between the two methods for handling the perturbative series. So if you do an average of both procedures, taking into account the differences and additional uncertainty, you get this number 0.328 plus minus 0.013, which appears at the end. I will not review all the information that is in this table. Everything is in our paper explained in full detail. So I will just want to comment in a few special points. First, the Aleph field. So we just did the fit of Aleph, and we found results which are in perfect agreement with them. Maybe our errors are slightly more conservative, but the differences are not really important. In the table, by the way, I have only shown results obtained with the full vector plus axial distribution. But you can also do separate analysis with the vector channel, with the axial channel, or with the sum, and you find consistent results in all cases. You also find that you have a very good sensitivity to alpha S, this is to be expected, and a very bad sensitivity to power correction, which is not surprising because power corrections are a small correction. So if you change something in your analysis, the central values of your power corrections can change by a quite sizable factor, but the sensitivity of alpha S to those changes is quite small. So here you see what you get from O6, you get from O8, and you get from alpha S. You can also see that the theoretical prediction that the O6 correction for the vector and axial channel comes with opposite signs and there is a big cancellation. It happens. What is more surprising is that you also find the same for dimension 8. This was not predicted, it's just the result of the field. In addition, those are the uncertainties that you get for the separate fields. The best results are obtained in the most inclusive channel, that is vector plus axial. The final errors were increased with the systematic uncertainty of the missing order 10 contribution, which means that we redid the fit, we included order dimension 10 corrections, and we included the difference in the uncertainty. And that's the final result. We quoted 0.329 with this uncertainty, which agrees perfectly well with the result of the Aleph people. It's just that the error is large. Okay, I will not show other methods, but let me show tests which are not used in the determination of alpha S. They are just used as a consistency test. So what is shown here? Here you are taking different weight factors, 1 minus x to the n power, with n equals 0, 1, 2, and 3. That means from 0 pinching to quite a lot pinching with n equal to 3. So if you don't put any weight factor, that's what n equal to 0 means, then you are just integrating the spectral function and nothing else. Therefore, you are extremely sensitive to your problems with the operator product expansion in the real axis. So that's why this we have never used to determine alpha S. We believe it's very, very dangerous. But in any case, you see here the integrals that you get from experiment. The red points are experiment data in the vector channel. The green points are experimental data in the axial channel. The black points are experimental channel in the full vector plus axial channel. And what you see in the bands is the pure perturbation theory prediction without any non-perturbative uncertainty, just with the value of alpha S that has been extracted from the field. And the result is surprisingly good. It's much better than one would expect before doing that. There are no power corrections from the operator product expansion. In fact, you will not expect the operator product expansion to work here, or n equal to 0. But you can see a beautiful duality violation, which is those wiggles in green and in red, that they go very fast to 0, and then at the tau mass scale, that means above 3 GeV, vector axial and vector plus axial agree very well. Everything agrees with the perturbative prediction. Okay, and this duality wiggle has disappeared. If you go to 1 pinching, n equal 1, you find something similar, but now the wiggles went to lower values. You have a much larger plateau where vector axial and vector plus axial agree with the perturbative prediction. Remember, non-perturbative corrections have not been included there. And here, for instance, you need to see the gluon condensate correction. You don't see it, it's too small to see it in your plot. What you see are two wiggles that again show you duality violation corrections, which appear at low S values and which tend to cancel in B plus A. They have opposite sign for vector and axial. Now you go to the plots with two pinch factors, n equal 2. The wiggles have disappeared. You don't see any duality violation effect anymore. You see a nice agreement of vector axial and vector plus axial at high S. And at low S, you clearly see a non-perturbative correction with the dimension 6. So you are seeing here that you are missing the dimension 6 condensate. And in addition, you see that it has opposite sign for vector and axial, and which compensate to some extent in vector plus axial. Again, in the other plot, n equals 3, you see the same effect, but now you are missing dimension 6 and dimension 8. And again, you see that the non-perturbative correction that you are missing in the plot has the behavior that you would expect. Another amazing table is you just take moments that are only sensitive to one or two condensates and nothing else. So the left part of the table are moments which are only sensitive to one condensate. The right-hand side of the table are moments which are only sensitive to two condensates. And you change the power so that in each row, the sensitivities to different condensates to different dimensionalities. And you fit alpha S without including any non-perturbative correction. And you fit alpha S at the tau mass scale. And what you find is that perturbation theory does a very good job, a surprisingly very good job. You don't see the power corrections. You can then plot the same analysis in terms of S0. So now you go down from the tau mass scale to values of S0 as low as 1 GeV. You are only showing the experimental uncertainties. Okay? The distribution does not contain any non-perturbative correction. So you are just extracting alpha S from experiment and pure perturbation theory. When you go to low values of S0, you should see that each color that corresponds to a different pinch factor, a different weight factor, should blow up with a different power of 1 over S0. And this does not happen. This just means that the non-perturbative corrections that you are missing are really very small. Okay? But these are only plots that illustrate what is going on. None of these exercises has been used to fit alpha S and to give the final result for alpha S. Let me now analyze another method. As I told you, we have analyzed all methods that people used before our paper. So this is using models of duality violation. Now what you want to see is the OP is not everything. So you really want to touch what happens when you go to the real axis. And you want to see what is the difference between the real correlator and the operator product expansion gives. So you take the difference, and using analyticity, you can relate this difference to an integral between S0 and infinity of the difference of the spectral functions between the OP and the physical spectral function. Okay, and this is a small correction that you are missing. Of course, if you are using weight factors with vanish at S0, you are completely suppressing this correction numerically. That's what pinching does. What Boyko told me,
you're running a bit out of time, Tony.
No, I need just 5 minutes, and I started just 20 minutes later. So,
well, you've been talking for 27 minutes now, so
okay,
3 more, but then we will not have time for questions now. Okay.
In 5 minutes, I finish. So what Boyko et al. Use, they just parameterize a form for this duality violation correction. That means you are making a guess of what the spectral function should be, and they just fit that from experiment. So what they do in technical terms is they do a fit of integrals without any weight factors. That means omega is equal to 1. And they fit between some low value of S0 that they take typically at 1.5 GeV squared. And then they fit bin by bin, all bins where you have data. Of course, you are fitting the derivative of the integral of the spectral function. So you are fitting the spectral function itself. So what this means is that you are fitting bin by bin the spectral function. So you fit these 4 parameters where the OP is not valid, but that's not important. It's just a fit. And then you are using the first bin, and the first bin happens to be at 1.2 GeV to determine alpha S. So the problem is that alpha S gets determined at the very low scale, 1.2, not at the tau mass scale. And that means large theory uncertainties. You can add additional weights, but of course you are not going to fit the spectral function itself. It's the same experimental information. The additional information that you get are the weighted integrals at the low value 1.2 GeV, and from there you get the condensates. So we repeat the exercise, we found the same results they found, and this is the value they are advocating, this value of alpha S, and you see how it changes with SC. The fit has instabilities. They have improved that in the more recent paper, so I will not enter into that, but of course you can argue what is the model dependence, because you are using an answer. So you just change the answer a little bit, and that's what you find. You find that the alpha S value that you extract is extremely sensitive to the answer that you are using. And as the fit improves, alpha S increases. It's not a large effect. I mean, alpha S is always a reasonable parameter in all fits you do. But of course, if you take into account this variation, your uncertainties are much larger than usually quoted. If you plot the spectral function, this is the fitted region, okay, where you fit the data. This is how this behaves in the original fit. It behaves very badly. What it happens when the fit goes improving and alpha S grows is that you are approaching more and more the data. This is not very important here. What is important is that the wiggles after the data that you have fitted get small. If you take into account, in addition, because here I am just putting data fixing S0. If I take into account the small variations of S0, the uncertainties are 3 times larger. What happens with the condensates you fit? Exactly the same. The small variation in the spectral functions changes completely the condensates you are getting. And this change is obvious where it comes from, is because you are extremely sensitive. You are fitting things at 1.2 GeV. The theoretical uncertainties there are very, very large. We can understand that with these plots. What they are doing corresponds to the plot, to the top plot in the left, this n equal to 0. This is the integral they are plotting. They are extracting alpha S from the point where the arrow lies. This is 1.2 GeV in energy scale. The normal approach to extract alpha S extracts alpha S at the tau mass scale, which is much, much larger. Okay? At the tau mass scale, you don't run into problems. Here, you run into many problems. In addition, you can see that, of course, perturbation theory gives the same result for vector, axial, and vector plus axial. But at this point, it just happens that experiment also gives the same result. So you need to correct experiment with some correction that clearly needs to be different because the vector, the axial, and the vector plus axial spectral functions have different wiggles in the region where you fit them. But at the end, you need to get exactly the same duality violation correction, which means you have a fine-tuning of parameters, and the fit is very unstable. I will not comment more into that. Let me just show plots, because since we pointed out this problem, then there have been many plots shown in the literature, which look surprising to me. You are supposed to read these plots as a comparison between 2 methods, where in the left-hand plot, you see something which is extraordinarily good. In the right-hand side, you have something that is very bad. But of course, you should ask what is being plotted. The second question is why it's only plotted in a given region above 1.5 GeV squared. The third question is why the theoretical errors are not there. and why the vertical scales are so tiny. So let me address these questions. What is plot is the difference between the integrated functions fitted and the value you get at the tau mass square minus the value you get at some value S0, and you fit that at S0 between 1.5 and 3. So all plots go to 0 at 3 by construction. But in the left plots, you should realize that you have fitted alpha S at S0 hat that is 1.5. So you have fitted things at 1.5, and you have fitted the spectral function. So once you have done that, then all values at every value of S0, the result of these integrals is fixed by your fit. So you are not testing anything related to alpha S. Okay? Therefore, the only thing that you are testing is that your fit is not bad, it's good. Therefore, the left plots don't provide any useful information concerning alpha S. In the right plots, you can ask where are the errors. Remember here, the errors, which are just pure perturbative errors, but they are there. And look to the scales, and look to the size of the errors. Look here to the scales. Okay, the scales are much smaller. It's clear that the perturbative errors are much larger than what is shown here. But if I just take one correction that is common to all these plots, that is the correction induced by the dimension 8 condensate, and I just take the uncertainty that appears in our alpha S determination, that what is supposed to be used at the tau mass scale, these are the theoretical uncertainties that you should put in these plots. I will not comment more on that. Those plots are completely misleading. We don't learn anything useful from them. So let me show the real plots. That's what you get without theoretical errors, experiment compared to the upper prediction, okay, without theoretical errors. Those are the parametric 1 sigma bands that you get, putting all correlations into account. They are not bad, but they are just parametric. And now you need to add the systematic uncertainties. Just, for instance, the systematic uncertainty that we put for the missing dimension 10 condensate amounts to doing that. So it moves from the blue line to the lines on the top. So this
sorry, you are really over time a bit now.
I finish. Okay. Of course, we could do much better. We could fine tune our fit to fix this condensate, but that's not the idea. We want to get reliable uncertainties on alpha S, and that's what we did without fine tuning the fits. So let me summarize. That's the result we get. It agrees very nicely with the ALET result. It agrees also nicely with the result that Cesar Ayala will present in a moment. It's very consistent, very reliable, very solid, I will say. And what for me is more important is that when you compare this value with the determination of the Z mass scale, it provides a beautiful test of asymptotic fit. Thank you very much.
Okay, thank you very much. Will you be there for the discussion session?
Sure.
Okay.